Look at our world, a familiar sphere of deep abyssal blue and vibrant sprawling green and brown. 6 distinct continents, adrift in the silent, patient expanse of 5 great oceans. This is the Earth we know, the planet we have mapped and measured and memorized since our very first glance at a globe or an atlas. It is the foundation of our geography, the stage upon which all of human history has unfolded. But this arrangement, this seemingly permanent configuration of land and water, is merely a snapshot, a fleeting moment in the incomprehensibly vast timeline of our planet's existence. The Earth, you see, is not a static object. It is a living, breathing, and endlessly dynamic entity. For 4.5 billion years, it has been in a constant state of transformation, a cosmic sculptor, forever reshaping its own surface. There have been epochs buried deep in time, when the planet was a sphere of ice, a snowball hurtling through space, its continents groaning under the weight of glaciers miles thick. And there have been other eras, equally alien to us, where the poles were lush and green, free of any ice, and the oceans swelled to levels we can scarcely imagine. In this grand planetary ballet, the most dramatic performers have always been the continents themselves. These colossal rafts of rock are not fixed in place, they are wanderers, drifting across the face of the deep. Driven by forces that originate in the very heart of the world, they have collided with unimaginable force, thrusting jagged mountain ranges towards the heavens. They have rifted apart, creating new oceans in the process, and sometimes, in rare and momentous periods of geologic history, they have come together. Imagine a world without the Atlantic Ocean, a world where you could, in theory, walk from the shores of what is now North America, directly into the lands of what is now Europe and Africa. Imagine a world with no Indian Ocean, no Pacific separating Asia from the Americas. Imagine all the lands, all the continents we know today, and some that have long since vanished, gathered together into a single colossal landmass, a true supercontinent. This world is not a fantasy, it was real. About 335 million years ago, this is precisely what the Earth looked like. This singular continent, a gargantuan puzzle of assembled land masses, has been given a name by scientists, a name that perfectly encapsulates its magnificent scale. They called it Pangea. The name is derived from ancient Greek, pan meaning all, and Gaia, or G, meaning earth or land. Pangea, all earth. For a time it was nearly all the earth that was land, concentrated in one hemisphere, and surrounding this immense continent was a single planet-spanning ocean, an equally super-ocean, named Panthalassa, meaning all sea. This was a different planet. The climate was a thing of extremes. Unlike anything in our modern experience, the very air had a different composition, and the life that crawled and grew upon its surface was utterly alien. Vast deserts of red sand stretched for thousands of miles in its interior. Strange, resilient plants, precursors to the conifers we know today, clung to life in a world often starved of rain. And the animals. This was not yet the age of the dinosaurs. Not at first. It was an age of bizarre amphibians, some the size of crocodiles, and strange mammal-like reptiles who were the dominant terrestrial creatures on the planet. This was the world of Pangea, a world that existed for over 100 million years, a world that looked as if it would exist forever. But the same titanic forces that brought it together would eventually tear it asunder. Around 200 million years ago, this mighty supercontinent began to crack, to fracture. Deep fissures, bleeding magma from the planet's molten heart, tore through its crust. The land began to stretch and thin and finally to break apart. The pieces, the continents we know today, began their long, slow drift away from each other, a process that continues to this very day. The Atlantic Ocean was born in the wound of its separation. The continents moved into the positions we find them in now, and in their wake the world we recognize was born. To conceive of this, to imagine the sheer power required to push and pull entire continents across the globe like pieces on a chessboard, is to grapple with a force and a timescale that dwarfs human comprehension. It is a story written not in books but in the very rocks beneath our feet, in the shape of our coastlines, the structure of our mountains, and the fossilized remains of creatures that lived and died on a world that no longer exists. This is the story we are going to explore. We will travel back in time to walk the strange landscapes of Pangea. We will witness its birth, its life, and its violent, world-altering death. But first we must ask a fundamental question. How do we know any of this? How did humanity first stumble upon the radical, almost unbelievable idea that the continents themselves could move? The journey to understanding Pangea begins not with a satellite or a supercomputer, but with a simple map and with the curious gaze of people who dared to notice something that was in hindsight, hiding in plain sight. For centuries, as the age of exploration dawned, and mapmakers began to chart the globe with increasing accuracy, a curious feature became apparent to anyone who studied the emerging picture of the world, a peculiar, almost deliberate symmetry. The great English philosopher and scientist Francis Bacon, as early as the year 1620, noted the uncanny parallelism between the western coast of Africa and the eastern coast of South America. It was more than a vague resemblance. It was a jigsaw puzzle fit. A bulge on one continent seemed to correspond perfectly to a bite on the other. It was an observation, an interesting little riddle, but nothing more. The technology and the scientific framework to explain it simply did not exist. Over the next 200 years, others would notice it as well. Thinkers and naturalists on both sides of the burgeoning Atlantic would comment on the strange congruence. But the prevailing view of the Earth was one of permanence. The continents and oceans were seen as primordial features, fixed in place since the planet's creation. The land might rise or fall slightly. Mountains might be thrown up by catastrophic events or worn down by erosion, but the fundamental geography was static. To suggest otherwise was to venture into the realm of pure fantasy. The continents were made of solid granite, anchored deep into the planet's interior. The idea that they could somehow plow through the solid rock of the ocean floor was quite simply absurd. The intellectual dam began to show its first cracks in the mid-19th century. Scientists were uncovering a world far older and more dynamic than previously imagined. The fossil record was revealing a succession of strange life forms, of extinctions and creations that spoke of immense spans of time. Geologists studying rock strata were piecing together a history of dramatic environmental change. In this environment of burgeoning discovery, an Italian-American geographer named Antonio Snider Pellegrini, in the year 1858, did something remarkable. He not only noted the fit between Africa and South America, but he also pointed out that coal deposits in both Europe and North America shared identical fossilized plants. To explain this, he produced two maps. The first showed the Americas nestled snugly against Africa and Europe, forming a single landmass. The second showed the continents in their present positions after having been torn apart by the biblical Great Flood. His mechanism was wrong, tied to religious catastrophe rather than scientific process, but the image he created, the image of the continents united, was a powerful and prophetic one. Yet, these were still just whispers at the edge of mainstream science. The established geological community, particularly in Europe and North America, built its understanding on the theory of a cooling, contracting Earth. The planet, they believed, was like a drying apple. As its molten interior radiated heat into space and cooled, the entire globe shrank. This contraction caused the crust to wrinkle, and these wrinkles were the world's mountain ranges. The lower areas, the parts that sank, became the ocean basins. It was a neat, mechanical, and widely accepted model. It was also, as we now know, fundamentally wrong. The stage was set for a revolutionary path. Someone with the intellectual courage and interdisciplinary vision to connect the scattered clues, the puzzle piece coastlines, the matching fossils, the strange continuity of mountain ranges across vast oceans, into a single cohesive and earth-shattering theory. That person was not a geologist, which was perhaps the key to his insight. He was a German meteorologist, an Arctic explorer, and an astronomer. His name was Alfred Wegener. Alfred Wegener's journey began, as many great scientific leaps do, with a moment of simple observation. The story, as told by Wegener himself, is that the initial spark occurred around 1910, He was in his study, looking at a New World atlas, like Bacon and others before him. He was struck by the fit of the continents across the South Atlantic. But for Wegener, this was not just a casual curiosity. It was a question that lodged itself in his mind and refused to let go. He described it as an immediate impression, an idea that felt strangely compelling even without proof. At first he dismissed it as an improbable fancy. The idea was too radical, too contrary to everything he had been taught. But the seed had been planted. Then, in the autumn of 1911, a new piece of information fell into his hands that would change everything. He came across a scientific paper that summarized the paleontological evidence for a former land bridge between Brazil and Africa. The paper discussed the discovery of identical and very specific fossils of plants and animals on these two widely separated continents. The conventional explanation at the time was the existence of vast sunken land bridges. It was proposed that massive continents had once existed in the oceans, a lost continent of Atlantis in the Atlantic, or Lemuria in the Indian Ocean, which had provided corridors for life to spread, before conveniently sinking beneath the waves without a trace. Wegener found this explanation deeply unsatisfying. It seemed ad hoc, an invention designed to solve one problem, while creating an even bigger one. Where did these immense land masses go? There was no evidence for their sunken remains on the ocean floor. Wegener saw a much simpler, more elegant solution, a solution that didn't require inventing phantom continents. What if the lands themselves had been joined? What if Brazil and Africa were once part of the same landmass and had since drifted apart? For Wegener, it was a moment of profound revelation. He wrote to his future father-in-law, "If it turns out that sense and meaning are now becoming evident in the whole history of the Earth's development, why should we hesitate to toss the old views overboard?" He began to search, methodically, and with a passion bordering on obsession, for every piece of evidence he could find from every scientific discipline he could access. He was a meteorologist, an expert on climate, but he dove headfirst into geology, paleontology, and geophysics. He was assembling the ammunition for an intellectual war. On January 6, 1912, at a meeting of the German Geological Association in Frankfurt, the 31-year-old Alfred Wegener stood before the assembled experts and presented his theory of continental displacement. He argued that the continents were not fixed. He proposed that they were rafts of lighter crust, which he called silo, floating on a denser, deeper layer, which he called cyma, and he declared that in the late Paleozoic era, all of these continents had been grouped together into a single supercontinent. He called it, for the first time, Pangea. The reaction was not just skeptical, it was hostile, it was scornful. The geologists in the audience saw Wegener as an outsider, a weatherman dabbling in a field he did not understand. Who was he to challenge a century of established geological doctrine? His ideas were dismissed as the delirious ravings of a madman. One prominent German geologist scoffed that his theories were nothing but moving crustal castles in the air. An American paleontologist called the theory utter damned rot. The criticism was often personal and vicious. He was accused of shoddy scholarship, of cherry-picking data, of being a dilettante. The core of the scientific objection, however, was not just professional jealousy or dogmatism. It was aimed at the greatest weakness in Wondrous, the mechanism. Wegener had presented a compelling case that the continents had drifted, but he could not provide a convincing explanation for how. What conceivable force could be powerful enough to shove a landmass the size of South America across the planet? How could a continent made of relatively brittle granite plow its way through the dense solid basalt of the ocean floor without shattering into a million pieces? The physics just didn't work. Wegener, in his desperation to provide a driving force, proposed two possibilities. The first was a force he called Polflucht. The second was the tidal pull of the sun and the moon. He argued that over millions of years, these gentle gravitational tugs could have dragged the continents westward. His opponents, who were expert physicists, immediately tore these arguments to shreds. They demonstrated, with incontrovertible mathematics, that the forces Wegener proposed were many orders of magnitude too weak. The centrifugal force was negligible, and for the tidal forces to be strong enough to move continents, They would have to be so powerful that they would have stopped the Earth's rotation entirely within a few years. Jenner had built a beautiful case file, full of circumstantial evidence, but without a murder weapon, without a credible mechanism. The jury of the scientific establishment would not convict. His grand theory of continental drift was cast out, relegated to the fringes of respectable science, considered a cautionary tale of speculative excess. But Jenner was not a man easily dissuaded. Convinced of the fundamental truth of his vision, he did not surrender. He spent the rest of his life tirelessly gathering more data, refining his arguments and publishing new editions of his landmark book, The Origin of Continents and Oceans. He knew that the evidence from the Earth itself was his greatest ally, and the most intuitive piece of evidence, the one that had started it all, was the geological and geographical fit. Let us return to that map, the one that so captivated Wegener. Let us look closer with the eyes of a geologist. The fit between South America and Africa is not just a party trick. It is stunningly precise, especially if you look not at the modern coastlines which are constantly being altered by erosion and changing sea levels, but at the true edge of the continents, the submerged continental shelves. In the early 1960s, long after Wegener's death, a British geophysicist named Edward Bullard used a computer, a new and powerful tool Wegener never had, to plot the fit of the continents at the 500-fathom line. The result was breathtaking. The overlap was almost non-existent. The continents locked together with a precision that defied coincidence. But the evidence goes far deeper than just the shape. Wegener pointed to the geology of the rocks themselves. He showed that ancient rock formations known as cratons, which are the stable primordial cores of continents, matched perfectly across the Atlantic. A specific 2-billion-year-old craton in West Africa, for instance, is truncated at the coast. It simply stops. Across the ocean, in Brazil, a craton of the exact same age and composition appears, as if it were the other half of a broken stone tablet. This was not a generic similarity. It was a precise match of rock type, age, and chemical signature. And then, there are the mountains. This was perhaps Wegener's most compelling geological argument. Mountain ranges are not random features. They are the scars of ancient continental collisions. Wegener demonstrated that if you reassembled the continents into Pangea, several ancient mountain chains, now separated by thousands of miles of ocean, would snap back together into a single continuous belt. Consider the Appalachian Mountains of eastern North America. They are a familiar ancient range worn down by hundreds of millions of years of erosion. They run up the coast and disappear into the sea off the coast of Newfoundland. Now travel across the Atlantic Ocean. In Ireland, in Scotland, and in Scandinavia, you will find mountains of the exact same age with the exact same type of folded rock structures and containing the exact same suite of minerals. These are the Caledonian Mountains. When the continents are reassembled in a Pangea configuration, the Appalachians and the Caledonians link up perfectly. They become one single magnificent mountain range, a range that marked a collision between ancient North America and ancient Europe, long before the Atlantic Ocean ever existed. To the geologists of Wegener's day, this was a staggering coincidence. They were forced to argue that two identical mountain ranges, with identical histories, just happened to form on opposite sides of a vast ocean at the same time. Wegener's explanation was far more logical. They weren't two mountain ranges, they were one, a single range, a single scar that was later ripped in two when Pangea fractured and the Atlantic was born. He found other, similar connections, a distinctive series of rock layers in South Africa, known as the Cape Fold Belt, terminates at the coast. Across the water, in the vicinity of Buenos Aires in Argentina, an almost identical sequence of rocks appears, with the same folds and the same history. The evidence was everywhere he looked. It was as if he had found two halves of a torn newspaper, and could show that not only did the edges match, but the very lines of text ran continuously from one piece to the other. The physical land itself was telling a story of union and of violent separation. The shapes of the continents, the nature of their ancient rocks, the continuity of their long-dead mountains, all of this was powerful testimony. It was the first pillar of proof for the lost world of Pangea. Yet, this was only the beginning of the evidence. The silent stones spoke of ancient connections, but an even more powerful and evocative story was waiting to be told. The story told by the dead, by the fossilized remains of the plants and animals that had once lived and thrived upon this single unified landmass, completely unaware of the oceans that would one day separate their graves. The story of life on Pangea would provide the next crucial chapter in this scientific revolution, a line of evidence that was, in many ways, even harder to dismiss. The stones of the earth had begun to speak. In the precise fit of the coastlines, in the ancient shattered mountain chains, the story of a former union was being whispered. Alfred Wegener had assembled a powerful geological case, one that suggested the continents were not immutable fixtures of our world, but rather wandering fragments of a long-lost whole. His arguments were logical, they were elegant, and they were almost universally rejected. The wall of scientific orthodoxy stood firm, built upon the foundation of a static earth, and for every piece of geological evidence Wegener presented, his critics had a ready answer, a counter-theory that, to them, seemed far more plausible than his wild fantasy of drifting lands. But Wegener's case was far from complete. He had another line of evidence to present, one that was, in many ways, far more difficult to explain away. He turned from the inanimate testimony of the rocks to the animate and far more evocative testimony of the dead. The fossil record, a library of stone, holding the imprints of countless creatures and plants that had lived and died across the unimaginable expanse of geologic time. And within this library, Wegener found a mystery, a biological impossibility that demanded an explanation. Identical species of land-dwelling animals and stationary plants were being discovered on continents, now separated by thousands of miles of deep, unforgiving ocean. How could this be? How could a small, crawling reptile built for life on solid ground exist in both southern Africa and South America? How could a fern, with seeds too heavy to be carried by the wind for more than a few miles, have spread its progeny across India, Australia, Antarctica and Africa? To the scientific establishment of the early 20th century, the answer was as colossal as it was convenient. Land bridges. They envisioned that in the distant past, immense continents had risen from the ocean floor, creating vast corridors between the lands we know today. Great isthmuses, like a prehistoric Panama, were thought to have stretched across the Atlantic and Indian Oceans, allowing life to migrate freely, and once their evolutionary purpose was served, these bridges, and indeed entire lost continents like the fabled Atlantis or the theoretical Lemuria, had simply sunk, vanished without a trace beneath the waves. The idea of Lemuria, for instance, was born from the curious distribution of lemurs and their kin, found in Africa, Madagascar, and parts of India and Southeast Asia. To explain this, the English zoologist Philip Sclater in the 1860s proposed a triangular continent that once occupied the Indian Ocean, connecting these now distant lands. The great German biologist Ernst Haeckel even suggested that Lemuria was the likely cradle of humanity. It was a compelling idea, an epic of a lost world, and for a time it was the only explanation that seemed to fit. It preserved the sanctity of fixed continents, while accounting for the strange distribution of life. But Alfred Wegener looked at this theory with the critical eye of a physicist, and he saw that it was impossible. He knew from geodetic measurements that the crust of the continents was fundamentally different from the crust of the ocean floors. The continents were made of a lighter, granitic rock he called Sile. The ocean floor was made of a denser, basaltic rock he called Cyma. For a land bridge, a continent, to sink, it would have to be forced down into a substance denser than itself. This violates the fundamental laws of buoyancy, the very principle of isostasy that keeps continents floating high upon the mantle. It is like expecting a great wooden ship to spontaneously sink to the bottom of a mercury sea. It simply does not happen. Furthermore, if these land bridges had existed and had subsequently foundered, where were their remains? The oceans are not bottomless pits. If a landmass the size of India had sunk in the Atlantic, its drowned mountains and plateaus should be detectable, but even the earliest, crudest oceanic soundings revealed no such thing. They showed deep abyssal plains and a great mountain range running down the center of the Atlantic, but no sign whatsoever of sunken continents. The land bridge theory was a phantom, a ghost invented to solve one problem, only to create a far greater physical one. Regina proposed his simpler, more radical solution. There were no sunken bridges. There were no lost continents. The bridges had been the continents themselves. The reason the fossils matched up across the oceans was because at the time these creatures lived and died, there were no oceans between them. Let us now walk through this evidence, piece by piece. Let us meet these silent, fossilized witnesses that Wegener called to testify on behalf of his theory. Our first witness is a small, unassuming creature, but its testimony is among the most powerful. Its name is Mesosaurus. Imagine a reptile, perhaps 2 to 3 feet in length. It had a long, slender body, a flattened tail for propulsion, and jaws filled with a thicket of long, needle-like teeth, perfect for snatching small crustaceans and fish from the water. Its feet were webbed, its bones dense. It was an aquatic creature, but it was not a creature of the open ocean. Detailed analysis of the rock in which its fossils are found and the nature of its skeleton tell us that Mesosaurus lived in shallow coastal waters, brackish estuaries and freshwater lakes. It was a creature of the shoreline, not the high seas. Now consider where its fossils are found. They are discovered in only 2 places on the entire planet. One is in the Karoo Basin of South Africa. The other is in the Paraná Basin of Brazil and Uruguay. These 2 locations are separated today by nearly 3,000 miles of the South Atlantic Ocean. And the fossils are not just found generally on these continents. They are found in a narrow, specific band of rock strata from the early Permian period, about 290 million years ago. If you push the continents of South America and Africa together, these 2 narrow bands of Mesosaurus fossils line up perfectly. How could this be? Could this small, freshwater reptile have undertaken the Herculean task of swimming across a proto-Atlantic ocean? It is inconceivable. It would be like a freshwater perch deciding to swim from the coast of Ireland to Newfoundland. It would not survive the journey. It would perish from the salinity, the temperature, the sheer exhaustion, and even if by some miracle one did, could an entire breeding population have done so to establish themselves on a new continent and in precisely the same type of environment they left behind? The odds are astronomically against it. The land bridge theory also fails here. If a land bridge had stretched across the Atlantic, one would expect to find Mesosaurus fossils all along its length, and perhaps in other areas where the bridge made landfall, but they are found nowhere else, only in this one, specific corresponding sliver of southern Africa and South America. Wegener's theory provides the only explanation that is both simple and profound. The reason Mesosaurus is found in these 2 places and nowhere else is that during the Permian period these 2 places were one. They were part of the same lake district, the same system of river estuaries. On the southern shores of Pangea, the Mesosaurus didn't swim across an ocean. It simply swam from one side of a lake to the other. The ocean formed later, splitting its homeland and its graveyard in 2. Let us call our next witness. This one is a more formidable creature, a powerful land-dwelling predator of the early Triassic period, about 250 million years ago. Its name is Cynomgnathus. Picture a creature perhaps the size of a modern wolf. Its name means dog jaw, and for good reason. It had a large skull, powerful jaws, and differentiated teeth with incisors at the front and shearing cheek teeth at the side. This was not a primitive reptile. It was a highly advanced synapsid, a mammal-like reptile that lies on the evolutionary line that would eventually lead to us. It was a fast, active predator, built for running down its prey on solid ground. It was, in every sense of the word, a terrestrial animal. The fossils of Cynomgnathus are found in South Africa, and they are also found in South America. Once again, we are faced with an impossible journey, a wolf-sized land-roving animal, somehow traversing thousands of miles of open ocean. The idea is patently absurd. No land bridge is needed to explain this. When Cynomgnathus was alive, hunting its prey across the Triassic landscape, South Africa and South America were joined. The plains of the Karoo were contiguous with the pampas of Argentina. It was all one hunting ground. The parade of witnesses continues. Let us meet one of the most important of all, a creature whose discovery in the coldest, most remote place on Earth would, decades after Wegener's death, provide the final, stunning confirmation of his ideas. The creature is called Lystrosaurus. Lystrosaurus was a survivor. It lived through the Permian-Triassic extinction event, the greatest mass extinction the world has ever known, and in the aftermath it became the most common terrestrial vertebrate on the planet. For a time, perhaps as many as 95% of all land animals were Lystrosaurus. It was a peculiar-looking herbivore, about the size of a pig. It had a stout, barrel-chested body and a strangely shaped skull. It had no teeth, save for two prominent tusks that grew down from its upper jaw, much like a walrus. It likely used these tusks for digging up roots and tubers. It was a slow-moving, land-dwelling, plant-eating animal. It was not a swimmer. It was not a traveller. Its fossils were first found in abundance in South Africa. Then they were found in India. Then in China. Already the map of its distribution was posing a problem for the fixists, but the true revelation was yet to come. Decades passed. Wegener's theory, while not forgotten, remained on the scientific fringe. Then came the 1960s, an era of new technology and new discoveries. In the austral summer of 1969, a paleontologist named Edwin Kolber and his team were searching for fossils in the desolate, frozen landscape of the Transantarctic Mountains. In the frigid air, at an altitude of over 6,000 feet, they made a discovery that would send shockwaves through the world of geology. They found a piece of a jawbone, a fossil. It was a fragment of the skull of a Lystrosaurus. Antarctica, a continent of ice locked at the bottom of the world, separated from Africa by the vast and stormy Southern Ocean. How did a pig-sized land-dwelling reptile get there? The discovery was electrifying. There was no conceivable way for Lystrosaurus to have crossed the thousands of miles of ocean to reach Antarctica. It couldn't have swum. It couldn't have clung to a raft of vegetation for months on end. The only rational explanation was that Antarctica itself had moved. Colbert's discovery of Lystrosaurus in Antarctica was hailed as one of the most significant fossil finds of all time. It was the keystone that locked Wegener's arch of evidence into place. The only way to explain the distribution of Lystrosaurus in Africa, India, and now Antarctica was if these three continents were once huddled together in a single landmass. A great southern continent, which Wegener and others had called Gondwana, which itself was the southern portion of the greater supercontinent of Pangea. The evidence from the animal kingdom was overwhelming, but the plants told the exact same story. Wegener's final star witness was not an animal, but a fossil fern, a plant known as Glossopteris. Glossopteris was a woody seed-bearing plant, a dominant feature of the southern landscapes during the Permian period. It was not a towering tree, but it formed vast dense thickets across the land. Its most distinctive feature was its tongue-shaped leaves, from which it gets its name, and crucially, it reproduced via seeds that were quite large and heavy. They were not seeds built for travel. They could not have been carried for thousands of miles by the wind. They could not have floated for years across saltwater oceans and remained viable. Yet the fossils of Glossopteris are found in one of the most widespread distributions imaginable. They are found in Australia, in Antarctica, in India, in southern Africa, and in South America. How could this single type of plant have colonized 5 continents, now separated by the world's greatest oceans? The land bridge theory collapses completely under this evidence. It would require a network of bridges connecting all of these southern continents into an impossibly complex web, and again there is no evidence for such a network. Wegener took a map, and he plotted the known locations of Glossopteris fossils. Then he cut up the map and moved the continents. He tucked the subcontinent of India into the space between Africa and Antarctica. He nestled Australia against the eastern edge of the Antarctic coast. He closed the Atlantic, bringing South America back against Africa. When he did this, the scattered, impossibly widespread distribution of Glossopteris suddenly coalesced into a single, contiguous, and perfectly sensible province. The fern hadn't crossed any oceans. It had simply spread across a single, unified landmass, Pangea. The fossil evidence was a narrative unto itself. It told a clear and consistent story, the story of a world without the oceans we know today, a world where animals could walk from Africa to Antarctica, where forests could stretch from Australia to India. It was a powerful and compelling case, but Wegener, the meteorologist, had one more card to play. He knew that the past was not only recorded in rocks and fossils, but also in the faint, lingering traces of ancient climates. He knew that the Earth's great climatic zones, the tropics, the temperate bands, the polar caps, are determined by the planet's rotation and its relationship to the sun. If the continents were fixed, then their climates, broadly speaking, should have been fixed as well. A continent near the equator should always have been tropical. A continent near the pole should always have been cold, but the geological record told a very different and very puzzling story. The story of climates gone haywire. The story of ice in the tropics and of lush tropical swamps in the Arctic. The paleoclimatic paradox. Consider the evidence for ancient ice ages. When a glacier, a vast river of ice, grinds its way across a landscape, it leaves behind unmistakable evidence. It deposits a unique, chaotic jumble of rocks and sediment known as till, and as it moves, the rocks embedded in its base cut deep, parallel grooves and scratches into the bedrock below. These are called glacial striations. They are the fingerprints of a glacier, and they show the precise direction of the ice's flow. During Wegener's time, geologists had found extensive evidence of a massive glaciation during the late Carboniferous and early Permian periods. Around 300 million years ago, they found thick layers of ancient hardened till called tillite, and they found bedrock covered in glacial striations, but the location of this evidence was deeply perplexing. It was found in South America, in southern Africa, in India, in Australia, all lands which today are largely temperate or tropical. How could there be continent-spanning glaciers in India, which now straddles the equator? Under the fixed continent theory, this would imply a global ice age of unimaginable severity, one that coated nearly the entire planet in a thick sheet of ice. But this was directly contradicted by other evidence from the very same time period. While these southern continents were apparently frozen solid, the northern continents were experiencing a warm, wet, tropical climate. In North America, in Europe, and in China, vast, steaming tropical swamps covered the landscape. These swamps would later form the great coal deposits that fueled the Industrial Revolution. This was the paradox. How could you have glaciers in the Congo Basin, while simultaneously having tropical rainforests in Pennsylvania and England? It made no sense. The climatic belts of the Earth seemed to be thrown into chaos. Alfred Wegener saw the solution with startling clarity. The problem wasn't that the Earth's climate was broken. The problem was that the map was wrong. He took his scissors and his glue pot to the map of the world once again. He reassembled the southern continents into the great landmass of Gondwana, the southern half of Pangea. When he did this, the scattered evidence for glaciation suddenly snapped into focus. The glaciated areas of South America, Africa, India, Australia and Antarctica all joined together, forming a single coherent ice sheet centered neatly over the South Pole. The puzzle was solved. The glaciers hadn't formed in the tropics. The tropics had moved away from the glaciers. The land itself had drifted north, away from the pole, carrying the scars of its icy past with it. The glacial striations provided the final, elegant proof. On a fixed map, the directions of ice flow indicated by the scratches in the rock were nonsensical. Glaciers in southern Africa seem to have moved onto the land from the ocean, which is impossible. But on Wegener's Pangean map, it all made sense. The striations all pointed outwards, away from the center of the great polar ice cap, showing the natural radial flow of a continental glacier. It was a stunning vindication. And what of the coal deposits? The evidence for tropical swamps in the far north? Wegener's model explained this just as elegantly. He showed that during the Carboniferous period, those parts of North America and Europe that were covered in coal swamps were not in their present northern latitudes. On the Pangean globe, they were located right on the equator. They were in the perfect position to host the lush tropical vegetation that would one day become coal. They had since drifted north, carrying their tropical inheritance with them to their current colder homes. The picture was now breathtakingly complete. The shapes of the continents fit together, the ancient rock formations and mountain ranges lined up. The fossil animals and plants showed a world without oceanic barriers, and the evidence of ancient climates, the ice and the coal, all fell perfectly into place on his new map. Wegener had presented a case built on a vast, interlocking web of evidence from a dozen different fields of science. He had shown that the Earth's past could only be understood if one accepted the mobility of the continents. The evidence was overwhelming. The logic was inescapable, and yet, for decades more, the scientific world refused to listen. They held fast to their static Earth, for despite the mountains of evidence that Wegener had piled up to show that the continents had moved, he still could not answer that one damning question that had haunted him from the very beginning. How? What force on Earth, or in the heavens, was powerful enough to accomplish such a feat? What titanic engine could drive entire continents across the face of the globe? This was the Achilles heel of his theory, and without a mechanism, his beautiful, elegant, and powerfully supported idea remained, in the eyes of most scientists, nothing more than a fascinating but ultimately impossible dream. The key to that final, crucial mystery lay hidden, buried in the one place no one had yet been able to properly explore: the deep, dark, silent floor of the ocean. The case was closed, yet the verdict was not guilty. Alfred Wegener, the persistent meteorologist, had presented a mountain of evidence. He had connected the continents with the unerring lines of their coastlines, the strata of their ancient rocks, and the ghostly continuity of their shattered mountain ranges. He had called forth witnesses from the deep past, the fossilized remains of creatures and plants, whose very existence on now distant shores defied all logic, unless those shores were once united. He had solved the baffling paradox of ancient climates, explaining with breathtaking simplicity how glaciers could exist in the tropics and tropical swamps could thrive in the Arctic. He had in essence described the scene of the crime in meticulous detail. He had shown the world what happened, but he could not produce the culprit, the mechanism, the force. The great earth-shattering engine that could drive continents across the globe remained a phantom, and without it, his grand, cohesive theory was dismissed by the mainstream of geology as a beautiful but impossible fantasy, a fairy tale, as one of his more charitable critics called it. And so for decades the idea of continental drift entered a long and lonely exile. Following Wegener's tragic death on the ice sheets of Greenland in 1930, his theory lost its most passionate and tireless champion. In the halls of academia, particularly in the geologically conservative institutions of North America, his ideas were not just debated, they were often ridiculed. They were held up as a cautionary tale, an example of speculative overreach, a warning to young geologists not to stray from the hard data of the rock hammer and the microscope into the dangerous wilderness of grand theory. The doctrine of permanence, of a static solid Earth with continents and oceans fixed in place since primordial times, reasserted its dominance. The textbooks were written, and Wegener was largely written out of them. But an idea this powerful, this elegant, this capable of explaining so much of the world's history does not simply vanish. It may be driven underground, whispered only by a few dissenters, but it waits for new evidence, or for a new generation of thinkers willing to look at the old evidence with fresh eyes. And during these wilderness years for continental drift, a few brilliant minds did indeed keep the flame of Wegener's revolution alive. One of the most important was a British geologist named Arthur Holmes. Holmes was a towering figure in the geology of the early 20th century. He was a pioneer in the use of radiometric dating to determine the age of rocks, effectively giving the Earth its proper multi-billion-year-old birth certificate. Unlike so many of his contemporaries, Holmes was not dismissive of Wegener's work. He saw the profound explanatory power of a mobile Earth, and he understood that the single greatest obstacle was the lack of a plausible mechanism. While other geologists were scoffing, Holmes was thinking. As early as 1929, a year before Wegener's death, Arthur Holmes published a paper containing a truly revolutionary suggestion. He turned his attention away from the surface of the planet, away from the crust, and looked deeper into the vast, mysterious, and then unknowable region of the Earth's mantle. He proposed that the mantle was not a static solid layer of rock. He suggested that over immense geological timescales, it behaved like a fluid, a thick, viscous, incredibly slow-moving fluid. He reasoned that the mantle was being heated from below by the immense radioactive furnace of the Earth's core. This heat, he argued, would create colossal, slow-turning loops of circulation within the mantle, incredibly slow-moving but incredibly powerful. He envisioned a process that we now see every day in a pot of simmering soup on a stove. Hotter, less dense material from the bottom rises. As it reaches the top, it spreads out, cools, and becomes denser. This denser material then sinks back down, only to be heated and rise again. Holmes proposed that these were the engines of the continents, these enormous rotating systems of flow within the mantle, which he termed convection currents, would exert a powerful dragging force on the underside of the continental plates above. Where two currents were rising and diverging, they would stretch the crust, thin it, and ultimately rip it apart, creating new oceans and pushing the continents away from each other. Where the currents were converging and sinking, they would drag the continents together, causing them to collide and crumple up into great mountain ranges. It was the answer. It was the powerful, planet-scaled engine that Wegener had been missing. It explained how continents could be moved without having to plow through the solid ocean floor. Instead, the continents were simply passengers, carried passively on the back of this immense, subterranean conveyor belt. But in 1929, this was a theory born almost entirely of logical intuition. There was no way to prove it. No one had ever seen the mantle. No one could drill deep enough to measure these supposed currents. Holmes's idea was brilliant. It was prescient, but it was untestable with the technology of the day, and so, while it was respected, it did not change the prevailing view. It remained a clever hypothesis, filed away in the scientific literature, waiting for its time. At the same time, in the southern hemisphere, a South African geologist named Alexander Du Toit was becoming Wegener's most devoted and important disciple. Du Toit was not a theorist like Holmes. He was a field geologist of extraordinary skill. He spent decades of his life trekking across the rugged landscapes of South America, Africa, India, and Australia, observing the rocks with his own eyes. He saw the evidence for Pangea not on a map but etched into the very cliffs and valleys of the southern continents. Du Toit gathered a wealth of new, more detailed geological evidence that supported Wegener's original claims. He refined the picture, showing with even greater precision how the rock formations and ancient climates of these lands matched up. He became so convinced of the former unity of the southern lands that he championed the name Gondwana for this southern supercontinent, a name originally proposed by the Austrian geologist Eduard Suess. Du Toit went on to argue that Pangea was not a single monolithic block, but was likely first composed of two great proto-continents, Gondwana in the south, and another landmass, Laurasia, in the north, which comprised ancient North America, Europe, and Asia. These two were separated by an ancient equatorial sea he called the Tethys. Du Toit's work was a monumental contribution. He added layers of detail and evidence that made the case for drift almost undeniable to anyone who studied the southern hemisphere. But even his immense body of field evidence could not overcome the stubborn skepticism of the northern hemisphere's geological community. The ghost of the mechanism problem still haunted the theory, and so the impasse remained. The world plunged into the chaos of the Second World War, and questions of ancient geology seemed to fade into the background. Yet it was this global conflict and the long, tense Cold War that followed that would paradoxically provide the very tools needed to unlock the planet's greatest secret. The next chapter in the story of Pangea would not be written by geologists with rock hammers, but by naval officers with cutting-edge military technology. The focus of the search would shift from the familiar ground of the continents to the dark, unknown, and mysterious world of the ocean floor. For all of human history, the seafloor had been a realm of utter mystery. It was a blank space on our mental map of the world. We knew its surface, the shifting, restless waves, but the world beneath was a place of imagination, of krakens and sea serpents, of crushing pressures and eternal darkness. Scientists in the 19th century had assumed it was a cold, quiet, and profoundly boring place. a flat, featureless abyssal plain, a dumping ground for the sediments that slowly washed off the continents over millions of years. They imagined it was an ancient, primordial landscape, largely unchanged since the Earth's formation. They could not have been more wrong. The key that unlocked the door to this hidden world was sound. During World War II, the terrifying effectiveness of the German U-boat fleet made understanding the submarine environment a matter of life and death for the Allied powers. They needed a way to detect submerged submarines and to navigate their own vessels safely through uncharted waters. The technology they perfected was the echo sounder, a system we now know universally as sonar. The principle was simple. A ship would send a pulse of sound, a ping, straight down into the water. This sound wave would travel to the sea floor, bounce off it, and return to a microphone on the ship's hull. By precisely measuring the time it took for the echo to return, and knowing the speed of sound in water, one could calculate the depth of the ocean at that point with remarkable accuracy. As a ship steamed along, it could send out a continuous series of pings, creating a continuous profile of the seabed topography beneath it. After the war, this military technology was released for scientific use. Oceanographic research vessels, crisscrossing the globe, began to map the ocean floor in earnest, and as the data poured in, a strange and utterly alien new world began to emerge from the darkness, a world that shattered every preconceived notion. The ocean floor was not flat, it was the most dynamic and dramatic landscape on the planet. The sonar charts revealed vast plains, yes, but they were cut by immense canyons and punctuated by thousands upon thousands of submerged volcanoes, which they called seamounts. Some of these seamounts had peculiar flat tops, as if their peaks had been sheared off. They were named guyets, and their existence was a puzzle in itself. Even more stunning were the discoveries of colossal mountain ranges. These were not small hills, but ranges that dwarfed anything on land. The greatest of these was found to be a single continuous globe-circling system of mountains that snaked its way through all the world's oceans for a staggering length of over 40,000 miles. It was the planet's seam. This was the mid-ocean ridge system. And running down the spine of this great global ridge, particularly in the Atlantic, was something even more remarkable. The charts revealed a deep, steep-walled valley, a great chasm, running right along the crest of the ridge, a rift. This is where our story narrows to focus on two remarkable individuals at Columbia University's Lamont Geological Observatory, Bruce Heezen and Marie Tharp. In the 1950s, Heezen was a senior scientist, leading expeditions to map the ocean floor. Marie Tharp was a geologist and draftsperson, working with the raw data that the research ships sent back. In that era, women were still barred from working on the oceanographic vessels, so while Heezen went to sea, Tharp stayed in the office, and it was she who had the monumental task of taking the endless columns of depth numbers and translating them into coherent profiles of the sea floor. As she meticulously plotted the data from the North Atlantic, point by point, sounding by sounding, she was the first human being to truly see the mid-Atlantic ridge in its full context, and she noticed something that no one else had. All of her profiles, taken from different ships over different years, showed the same feature, a deep V-shaped valley running right down the center of the ridge. It was persistent, it was real. She realized this must be a rift valley, a place where the Earth's crust was being pulled apart. She brought her discovery to Heezen. Heezen was a brilliant scientist, but he was a product of his time, steeped in the traditional non-drift geology. His initial reaction was famously dismissive. He reportedly examined her work and told her it was just girl talk. The idea of a rift valley implied a pulling apart of the crust, a mobility that smacked of Wegener's discredited continental drift, a theory Heezen did not subscribe to. He, like many others, initially believed in an expanding Earth theory to explain the ridges. But Tharp was persistent. She knew what the data showed. To bolster her case, she looked for an independent line of evidence. She got a map that plotted the epicenters of recent Atlantic earthquakes. She overlaid this earthquake map onto her map of the mid-Atlantic ridge. The result was a moment of pure scientific vindication. The earthquake epicenters fell perfectly within the boundaries of her rift valley. The earthquakes were happening inside the rift. This was not a dead, ancient feature. This was a place where the Earth was alive and actively tearing itself apart. When she showed this correlation to Heezen, he was stunned into silence. He could no longer dismiss her findings. This was undeniable proof. Together they began a collaboration that would change the face of Earth science. Over the next few years, they synthesized all the available data into a single spectacular physiographic map of the entire ocean floor. Published in 1977, this map revealed the full breathtaking majesty of the mid-ocean ridges, the deep ocean trenches, and the vast abyssal plains. For the first time, humanity could see the true face of our planet. The map was a masterpiece, a work of both science and art, and it hung on the wall of every geology department in the world. And at its heart was Marie Tharp's Rift Valley, the great scar where a new world was being born. The map showed what was on the ocean floor, but it did not by itself explain how it worked. That final crucial leap of imagination would come from another veteran of the Second World War, a geologist and former submarine commander from Princeton University named Harry Hess. During the war, Hess had commanded an attack transport ship in the Pacific. He had left his vessel's echo sounder running continuously, a habit that annoyed the Navy but delighted the geologist in him. He had mapped thousands of miles of the Pacific floor and he was haunted by its strange features, especially the mysterious flat-topped guyets. After the war, he pondered the new discoveries, the global ridge system, the deep trenches, the Rift Valley teeming with earthquakes. He also remembered Arthur Holmes's old, neglected theory of mantle convection. In 1960, Hess put all the pieces together in a paper he humbly called An Essay in Geopoetry. He laid out a theory of such elegance and power that it would become the very foundation of modern geology. He called it seafloor spreading. Hess proposed a beautifully simple model. The mid-ocean ridges with their central rift valleys were not wrinkles on a cooling planet. They were the sites where the great convection currents envisioned by Holmes were rising towards the surface. As the hot mantle material rose, it welled up into the rift, where it cooled, solidified, and formed fresh new oceanic crust. This process, he argued, was continuous. It was like a factory, constantly manufacturing new seafloor, and as new material was added at the center, it pushed the older rock away from the ridge on both sides. The entire ocean floor, Hess proposed, was moving away from the ridge crest in two opposing directions, like a pair of giant conveyor belts. This was the master stroke. This was the mechanism. Jenner had been wrong in one crucial detail. He had envisioned the continents as ships, plowing their way through the static, resistant ocean floor. This was the physical impossibility that had doomed his theory. Hess showed that this was not the case at all. The continents were not plowing through anything. They were passive passengers. They were being carried along, rafted on the back of the moving, spreading seafloor. The continents moved because the ocean floors moved. His theory also elegantly explained the other great mystery of the deep, the oceanic trenches. If new crust was constantly being created at the ridges, why wasn't the Earth expanding like a balloon? Hess proposed that there must be places where the old crust was destroyed. He identified these as the deep ocean trenches, the profound chasms that rimmed the Pacific Ocean. Here, he suggested, as the spreading seafloor reached the edge of a continent, it bent downwards and plunged back into the mantle, where it was remelted and recycled. He called this process subduction. It was a complete system, a global cycle of creation and destruction, birth at the mid-ocean ridges, a long, slow journey across the ocean basin, and death in the fiery depths of a subduction zone. It explained the youth of the ocean floor. No rocks older than 200 million years had ever been found, because the older rock had all been recycled. It explained the guyjotes. They were volcanoes that formed at the ridge, had their tops eroded flat by waves at sea level, and were then carried away from the ridge, sinking into deeper water as they went. It explained everything. It provided the engine for Wegener's drift. Hess's seafloor spreading hypothesis was the long-awaited key. It connected the evidence from the continents with the new dramatic evidence from the oceans. It provided the physical process that made continental drift not just possible, but inevitable. Yet in the cautious world of science, even a theory as beautiful as this one requires definitive proof. Hess had proposed a model, a brilliant one, but it was still a hypothesis. How could you prove it? How could you demonstrate that the seafloor was truly moving like a conveyor belt? The answer, the final smoking gun, would not come from sound waves or rock hammers, but from the faint, invisible ghost of the Earth's ancient magnetism, a ghost that was frozen and recorded in the rocks of the ocean floor, in a pattern so strange and so perfect, it would silence the remaining doubters once and for all. Harry Hess had offered the world a vision, a grand poetic concept of an ocean floor in constant motion, a planetary conveyor belt of creation and destruction that carried the continents as passive passengers upon its back. His hypothesis of seafloor spreading was the missing link, the elegant engine that Alfred Wegener's theory had so desperately needed. It was a beautiful idea. It connected the rising convection currents of Arthur Holmes's imagination with the stark, newly discovered topography of the mid-ocean ridges and the deep ocean trenches. It explained everything. And yet, in the rigorous world of science, elegance is not enough. A hypothesis, no matter how compelling, remains just a hypothesis until it is proven. It requires a prediction, a test, a piece of evidence so clear and unambiguous that it silences all doubt, a smoking gun. Hess had provided the theory, the how, but the world of geology, so deeply skeptical after 50 years of dismissing Wegener, now demanded proof. That proof would not be found by drilling a hole to the mantle, or by measuring the movement of the continents in real time, a feat that was still technologically impossible. The final definitive evidence for seafloor spreading, the discovery that would launch the theory of plate tectonics and complete Wegener's vindication, would come from an invisible force, a faint, ghostly presence that permeates our entire planet, a force that has been guiding travelers for centuries, but which holds a secret history of its own. It would come from the Earth's magnetic field. To understand this final, crucial chapter, we must first understand a property of our planet that is both familiar and deeply strange. The Earth itself is a magnet. Deep within its core, the churning motion of molten iron and nickel generates a powerful magnetic field, a dynamo of planetary scale. This field surrounds our world in a vast invisible cocoon, the magnetosphere, which shields us from the harmful radiation of the sun. On the surface, we experience it most simply with a compass. A small magnetized needle, free to pivot, will always align itself with the lines of magnetic force, pointing roughly towards the geographic poles. But this magnetic field is not just a navigational aid. It has the remarkable ability to become fossilized in rock. Many volcanic rocks, such as the dark, iron-rich basalt that makes up the entirety of the ocean floor, contain tiny, microscopic crystals of magnetic minerals, most commonly a mineral called magnetite. When lava first erupts, either on land or from a deep-sea volcano, it is a molten fluid heated to over 1,000 degrees Celsius. At this extreme temperature, known as the Curie point, the individual magnetic domains within the magnetite crystals are agitated and free to move. Like trillions upon trillions of microscopic compass needles floating in a liquid, they dutifully swing into alignment with the direction of the Earth's prevailing magnetic field at that moment. Then, as the lava cools and solidifies into hard rock, these tiny mineral compasses are frozen in place. Their magnetic orientation is locked in, permanently. The rock itself has become a fossil compass, a silent magnetic snapshot that preserves a precise record of which way was north at the exact time and place of its formation. This study of the Earth's ancient magnetism, locked away in its rocks, is called paleomagnetism. In the 1950s, long before the final seafloor mystery was solved, paleomagnetists began studying the magnetism of ancient lava flows on the continents, and they immediately ran into a series of profound puzzles. When they measured the magnetic orientation of rocks of different ages from the same continent, for instance North America, they found that the rocks did not all point to the current North Pole. In fact, rocks from 200 million years ago pointed to one position, rocks from 300 million years ago pointed to another, and rocks from 400 million years ago pointed to yet another. When they plotted these ancient pole positions on a map, it looked as if the Earth's magnetic North Pole had wandered, or drifted, all over the globe over geologic time. They called this phenomenon apparent polar wander. But this created an even deeper paradox. When their colleagues in Europe did the same thing, they also got a wandering path for the pole, but it was a different path. The North American path and the European path did not match. This was a physical impossibility. The Earth can only have one north magnetic pole at any given time. How could there be two different polar wander paths? For years, this was a major geological conundrum, but a few scientists, remembering Wegener, saw the beautifully simple answer. The pole had not wandered. The continents had. Imagine two people walking away from a single streetlight at night, each taking a different path. From each person's perspective, it looks as if the streetlight is moving, and their perspective of the streetlight's apparent motion will be different. But if you know their starting point, you can reconstruct their paths and show that the streetlight never moved at all. The scientists realized it was the same for the continents. There was only one North Pole. The reason there were two different polar wander paths was that Europe and North America had once been together and had since drifted apart. When they took their maps and slid the continents back together, closing the Atlantic Ocean as Wegener had proposed, the two separate nonsensical polar wander paths merged and became a single coherent path. It was a stunning independent confirmation of continental drift. But this was not the strangest discovery to emerge from the study of fossil magnetism. As geologists examined long layered sequences of volcanic rock on land, where lava flow had piled upon lava flow over millions of years, they found something that at first seemed to be an error in their equipment. Some layers showed a normal magnetic polarity, with the fossil compasses pointing towards today's north, but other layers, deeper down or higher up, showed a completely reversed polarity. The compasses within them pointed directly south. The finding was so bizarre that many were deeply skeptical, but as more and more data came in from different locations around the globe, the conclusion became inescapable. The Earth's magnetic field was not stable. Throughout its history, at irregular and unpredictable intervals, it had completely flipped. The North Magnetic Pole had become the South Magnetic Pole, and vice versa. A compass on the Earth hundreds of millions of years ago would have, at different times, pointed in opposite directions. This was a discovery of monumental importance. Using radiometric dating to determine the age of each lava layer, scientists could now build a precise timeline of these magnetic reversals. They could see that there were long periods of normal polarity, like the one we live in today, which they called crons, and these were punctuated by periods of reversed polarity. They began to build a reference, a barcode of geologic time, known as the magnetic polarity timescale. By the early 1960s, the history of these magnetic flips over the last few million years had been firmly established from rocks on land. And now, all the pieces were on the table. Harry Hess had proposed that the seafloor was spreading from the center, and on land, geologists had uncovered the wild history of the planet's magnetic reversals. The two ideas seemed completely unrelated, but it would take the insight of a few brilliant young minds to see that they were, in fact, two halves of the same perfect solution. At the same time these discoveries were being made, oceanographic ships were continuing their surveys, but now they were often towing new instruments behind them, magnetometers. These were highly sensitive devices that could measure the strength or intensity of the magnetic field emanating from the rocks of the ocean floor below. And when they plotted this data, another bizarre pattern emerged. The ocean floor's magnetism was not uniform. Instead, it was arranged in long linear stripes, running parallel to the mid-ocean ridges. Stripes of slightly higher than average magnetic intensity alternated with stripes of slightly lower than average intensity. More strangely still, this pattern was perfectly symmetrical on both sides of the ridge crest. If you found a wide stripe of high intensity, followed by a narrow stripe of low intensity at a certain distance east of the ridge, you would find the exact same pattern, a mirror image at the same distance west of the ridge. The ocean floor looked like a giant stony zebra. No one had any plausible explanation for this perfectly regular, perfectly symmetrical pattern. The solution, when it came, was an act of pure scientific synthesis, a moment of genius that connected all these disparate threads of evidence into one unified theory. It came in 1963 from two researchers at Cambridge University, A 25-year-old PhD student named Fred Vine and his supervisor Drummond Matthews. At almost exactly the same time, a Canadian geologist named Lawrence Morley independently came up with the identical idea, though his paper, in a now infamous decision, was rejected for publication as being too speculative. Their idea, which has come to be known as the Vine-Matthews-Morley hypothesis, was the smoking gun. It was the definitive proof of seafloor spreading. They started by accepting Harry Hess's idea as correct, that new volcanic crust is continuously being created at the mid-ocean ridge and is then carried outwards in both directions. Then they incorporated the second key idea, that the Earth's magnetic field periodically reverses its polarity. They reasoned as follows. As hot magma rises and erupts at the mid-ocean ridge, it cools and solidifies. The magnetite crystals within it align with the Earth's magnetic field at that moment, locking in a record of its polarity. Let us say this happens during a period of normal polarity, like today. This newly formed strip of crust will be normally magnetized, and as it moves away from the ridge, it carries that magnetic signature with it. Sometime later, perhaps hundreds of thousands of years, the Earth's magnetic field reverses. The new magma now erupting at the ridge will cool and solidify in a world where north is south and south is north. It will become a strip of reversely magnetized crust. This new reversed strip then begins to move away from the ridge, pushing the older, normally magnetized strip ahead of it. Then the field flips back to normal. The next strip to form will be normally magnetized. Then it flips again and the next strip is reversed. The result they predicted would be a perfect magnetic tape recording. The ocean floor itself was preserving the history of the Earth's magnetic reversals in a series of parallel, magnetized stripes. When a survey ship's magnetometer passed over a stripe of normally magnetized crust, whose magnetic field is aligned with the Earth's current field, the two fields would add together, producing a reading of slightly higher intensity. When it passed over a stripe of reversely magnetized crust, whose field opposes the Earth's current field, the fields would subtract, producing a reading of lower intensity. The zebra stripes were explained. They were not a feature of the rock itself, but a fossilized record of the planet's magnetic history, laid down on the spreading seafloor. The hypothesis also beautifully explained the symmetry. Since the seafloor spreads outwards from the ridge in both directions at the same rate, the pattern of stripes had to be a perfect mirror image on either side of the ridge crest. It was a breathtakingly elegant hypothesis, and better still, it made a clear and testable prediction. If the hypothesis was correct, then the pattern of wide and narrow magnetic stripes on the seafloor should exactly match the pattern of long and short magnetic reversal periods, already known from the dated lava flows on land. The test came quickly. In the mid-60s, data from a US Navy research vessel, the El Tarnin, which had been surveying a section of the Pacific Antarctic Ridge, produced a spectacularly clear, high-resolution magnetic profile. It was a clean, unambiguous set of zebra stripes. Scientists took this seafloor magnetic profile and placed it alongside the magnetic polarity timescale that had been built from rocks on land. The match was perfect. It was absolute. The pattern of the stripes was identical to the pattern of the reversals. The wide stripes on the seafloor corresponded to the long periods of normal or reversed polarity, and the narrow stripes corresponded to the short, fleeting reversals. This was it. This was the proof. The ocean floors were moving. Harry Hess was right. Arthur Holmes was right. And the biggest vindication of all belonged to the man who had died on the ice 3 decades earlier. Alfred Wegener was right. The discovery published by Vine and his colleagues in 1963 unleashed a firestorm in the world of earth science. It was a revolution in the truest sense of the word. Within less than a decade, the entire foundation of geology was overturned. The old static models were thrown out. The fixers either converted, often with great enthusiasm, or they quietly retired. A new unifying theory rapidly took shape, incorporating continental drift, seafloor spreading, and the new knowledge of the Earth's structure. It was given a new name, plate tectonics. This new theory was more comprehensive than anything that had come before it. It stated that the Earth's rigid outer layer, called the lithosphere, which includes the crust and the very top solid part of the mantle, is not a single continuous shell like the skin of an apple. Instead, it is broken into a mosaic of about a dozen large rigid plates and a number of smaller ones, all moving relative to each other. These plates are all floating on a hotter, softer, partially molten layer of the mantle beneath called the asthenosphere. And the grand slow dance of these plates explained everything. All of the Earth's major surface features and processes, earthquakes, volcanoes, mountain ranges, the very shape of the continents and oceans were the result of what happens at the boundaries where these plates meet. Scientists identified three fundamental types of plate boundaries. First, there are the divergent boundaries. These are the places where plates are moving apart. The prime example is the mid-ocean ridge system, the creative seam of the planet where new oceanic crust is being generated by seafloor spreading, pushing the plates away from each other. This process is not just happening in the oceans. When this rifting process begins under a continent, it starts to tear the land apart, forming great rift valleys, like the modern East African Rift Valley, which is slowly centimeter by centimeter, splitting the African continent in two. The second type are the convergent boundaries, the destructive margins where plates are moving towards each other. What happens here depends on the type of crust involved. When a dense oceanic plate collides with a lighter continental plate, the oceanic plate bends and plunges down into the mantle in a subduction zone. This process is incredibly violent. As the plate descends, it grinds against the overlying plate, causing the most powerful earthquakes on the planet. As it goes deeper, water baked into the oceanic crust is released, causing the overlying mantle to melt. This molten rock then rises to the surface to create chains of explosive volcanoes on the edge of the continent, like the Great Andes Mountains of South America. If two oceanic plates collide, one will subduct beneath the other, forming a deep trench and a chain of volcanic islands, an island arc like Japan or the Aleutian Islands of Alaska. This is the reason for the Pacific Ring of Fire, a vast horseshoe-shaped zone of intense earthquake and volcanic activity that traces the convergent boundaries of the mighty Pacific Plate. And finally, when two continental plates collide, the crust is too light and buoyant to subduct. Instead, the two land masses crumple, fold, and stack up on top of each other, creating immense, non-volcanic mountain ranges like the towering Himalayas, which are the result of the Indian Plate crashing, and still crashing, into the Eurasian Plate. The third and final type of boundary is the transform boundary, where plates neither converge nor diverge, but instead slide horizontally past one another. The immense friction between the grinding plates means that the movement is not smooth. The plates lock together for long periods, building up incredible amounts of stress, which is then released in sudden violent jerks, creating powerful earthquakes. The most famous example of a transform boundary on Earth is the San Andreas Fault in California, which marks the line where the Pacific Plate is grinding northwestwards past the North American Plate. With these three boundary types, the theory of plate tectonics provided a single, elegant, unifying framework to understand the workings of our world. It was the geological equivalent of Darwin's theory of evolution or Einstein's theory of relativity. It was the paradigm shift that Wegener had dreamed of. The revolution was complete. We finally understood the engine. We finally knew how the continents moved. And with this powerful new understanding, with this knowledge of the engine that drives the planet, scientists could now do something they had never been able to do before with confidence. They could rewind the tape. They could use the principles of plate tectonics to accurately reconstruct the past, to trace the long and epic journey of the continents. They could now begin to tell the full story, not just of Pangea's existence and breakup, but of its very creation. The next chapter in our journey would be to travel back even further, to witness the slow, colossal and majestic assembly of the greatest supercontinent the world had seen in an eon. We stand now at the summit of a great intellectual mountain. The long, arduous climb, which began with a simple observation of a map and led through decades of doubt, ridicule and painstaking discovery, is over. The theory of plate tectonics is our reward. It is the master key to our planet's past, its present and its future. We now understand that the ground beneath our feet is not solid and permanent, but a mosaic of immense rigid plates, drifting upon the slow, fiery currents of the mantle below. We know that these plates are born in fire at mid-ocean ridges, and they die in fire at deep subduction zones. We know that in their grand, silent and unending dance they carry the continents with them. With this extraordinary power of understanding, we are no longer limited to simply observing the present. We can now become geological chronauts. We can use the precise mathematical laws of plate motion to reverse the tape of history. We can command the Atlantic to close, watch the Americas nestle back against the shores of Africa and Europe, and see the world of Pangea reappear from the mists of time. But even this, the reconstruction of Pangea, is not the beginning of the story. The history of our planet is far grander, more ancient and more cyclical than that. Pangea, for all its magnificent scale, was not a unique event. It was but one chapter in a much larger epic. Earth scientists now understand that the assembling and dispersing of supercontinents is a recurring theme in our planet's life story, a colossal rhythm that beats over vast eons of time. This is the supercontinent cycle. Imagine, if you will, the continents adrift on the mantle like great wooden rafts on a thick, viscous sea. As they drift, they eventually begin to converge. Subduction zones form, ancient oceans are swallowed, and one by one the continents collide, welding themselves together into a single immense landmass. A supercontinent. But the very existence of this supercontinent sows the seeds of its own destruction. This colossal blanket of continental crust acts as a thermal insulator, trapping the immense heat escaping from the Earth's core. The mantle beneath the supercontinent begins to overheat, to swell upwards. The pressure builds over tens of millions of years, until finally the great landmass begins to stretch, to crack, and to rift apart. New oceans are born in the fissures, and the fragments, our familiar continents, begin to drift away from each other once more, scattering across the globe, only to begin, eventually, the slow process of reassembly on the other side of the planet. This cycle, this planetary pulse of assembly and dispersal, is thought to take somewhere between 300 and 500 million years. Pangea is simply the most recent iteration. Before Pangea, there were other giants. Geologists have found faint, ghostly traces of these lost worlds in the ancient rocks. There was likely a supercontinent named Panatosha, which existed around 600 million years ago. And before that, an even grander and more long-lived supercontinent named Rodinia, which dominated the globe over 1 billion years ago. Pangea's story is therefore not just the story of one landmass, but the story of the last time our planet's continents came together in their majestic cyclical dance. To truly witness the birth of Pangea, we must rewind the clock much further back. We must travel to a time long before its formation, to a world that would be utterly alien to our eyes. Let us set our temporal sights on the early Paleozoic era, roughly 550 million years ago, during the Cambrian period, a time of explosive evolution in the seas. What did the world look like then? It was a world of many continents and vast oceans. There was no Pangea. The future continents were scattered across the globe like a broken puzzle. The largest and most significant player on this planetary stage was a true behemoth of a continent, a landmass already far larger than any single continent today. This was the great southern supercontinent of Gondwana. It was a colossal raft containing the geological cores of what would one day become South America, Africa, Arabia, Madagascar, India, Australia, and Antarctica. In this ancient time, this giant landmass was centered over the South Pole, and much of it was covered in ice. Floating alone like great islands in a global sea were the other major players. There was Laurentia, a large continent that comprised the ancient heart of North America, along with Greenland and parts of Scotland. Laurentia was a tropical landmass at this time, sitting astride the equator, its shores bathed in warm, shallow seas teeming with the strange, early life of the Cambrian explosion. To its east, across a widening ocean, sat Baltica, the geological core of Scandinavia and Eastern Europe, and further still the continent of Siberia, which was also a lone landmass, rotated almost 90 degrees from its present orientation. And between these great landmasses were smaller, but no less important, pieces of the puzzle. There were microcontinents, fragments of crust that had broken off larger landmasses, such as Avalonia, a sliver of land that would one day become England, Wales, and parts of eastern North America. And there were volcanic island arcs, long curved chains of volcanoes much like modern Japan born from subduction in the middle of the ocean. These continents were separated by vast, now vanished oceans. The most important of these for our story was the Great Iapetus Ocean, which separated Laurentia from Baltica and Gondwana. The Iapetus was the precursor to the Atlantic, a wide and ancient body of water. To the west of Laurentia, and encompassing most of the rest of the planet, was the enormous Panthalassic Ocean, the superocean that would one day become the Pacific. This was our stage, a world of scattered lands and wide open seas. The assembly of Pangea is the story of how these oceans closed and how these separate lands were brought together in a series of titanic slow-motion collisions, each one lasting for tens of millions of years. Each collision, which geologists call an orogeny, threw up mountain ranges that would have dwarfed anything we know today. The first great movements in this tectonic ballet began in the north. The Iapetus Ocean, which had been widening, began to close. A subduction zone formed along its edge, and the ocean floor of the Iapetus began to slowly sink back into the mantle. Laurentia, Baltica, and the island arc of Avalonia were now on a collision course. The first to arrive was Avalonia, around 480 million years ago. This microcontinent, a sliver of crust that had originally broken away from the northern edge of Gondwana, slammed into the coast of Baltica. But the main event was yet to come. The floor of the Iapetus continued to subduct, pulling the larger continents of Laurentia and the newly amalgamated Baltica-Avalonia towards each other. The collision, when it happened around 420 million years ago, was an event of unimaginable scale and violence. It was not a sudden crash, but a slow, grinding, inexorable crunch that lasted for over 20 million years. As Baltica and Avalonia collided with the eastern coast of Laurentia, the edges of the continents, which had once been placid coastal plains, were now subjected to incomprehensible stress. The rock layers buckled, folded, and fractured. They were pushed up, one on top of another, creating immense sheets of rock called nappers. The pressure was so intense and the heat so great that the very nature of the rock was changed. Sandstones were transformed into glittering quartzites, and shales were metamorphosed into gleaming schists and sturdy gneisses. Deep beneath the surface, the immense heat melted parts of the crust, creating vast subterranean chambers of magma that slowly cooled to form massive intrusions of granite. The surface expression of all this geological violence was a mountain range, a colossal mountain range. This was the Caledonian orogeny and the mountains it created. The Caledonian Mountains were likely among the grandest the planet has ever seen. We must not picture the worn-down, gentle hills we see today in Scotland or Norway. We must imagine a range of jagged, ice-capped peaks, soaring to heights of 25 or even 30,000 feet, rivaling or perhaps even exceeding the modern Himalayas. This great chain of mountains, glowing red and orange under the ancient sun, stretched for thousands of miles, forming the backbone of a newly forged continent. The northern Iapetus Ocean was gone, and in its place stood a single unified northern landmass, sometimes called Euramerica, or the Old Red Sandstone Continent, after the distinctive red sediments that washed down from its mighty eroding peaks. The first major piece of Pangea had been assembled. But the world was still divided. To the south lay the still separate giant of Gondwana, between the new continent of Euramerica and the southern behemoth of Gondwana lay another ocean known as the Regic Ocean. For a time this ocean widened, but the engine of plate tectonics is relentless. New subduction zones formed, and soon the Regic Ocean too began to close. Gondwana, the great southern landmass, began a slow, majestic northward drift, heading for a final world-altering collision with Euramerica. This was to be the main event, the grand finale, the collision that would weld the northern and southern halves of the world together and truly form the core of Pangea. This was not a single clean event, but a complex series of collisions that unfolded over nearly 100 million years, from about 380 to 280 million years ago. Geologists call this vast and protracted mountain-building event the Variscan orogeny in Europe and the Alleghanian orogeny in North America. But it was all part of the same colossal crunch. Imagine the northwestern coast of what is now Africa, slowly, centimeter by centimeter, bearing down on the southeastern coast of what is now North America. The floor of the Jurassic Ocean was consumed beneath the continental margins, pulling the two landmasses together. As they met, the initial contact was likely a soft shearing collision with parts of Gondwana grinding sideways along the edge of Euramerica. But eventually the full force of the continental masses was brought to bear. The geological violence was even greater than that of the Caledonian orogeny. The continental margins, laden with thick layers of sediment washed into the Rhythmic Ocean over millions of years, were now caught in a tectonic vice. These sediments were scraped off the descending plate, folded, faulted, and thrust upwards into a new, even more magnificent mountain range. This was the central Pangean Mountains, the great suture that stitched the northern and southern continents together. At its zenith, this mountain range was a spectacle to rival any in Earth's history. It was a continuous belt of towering, alpine-style peaks that stretched for more than 5,000 miles. From what is now Mexico, the mountains ran through the southern United States, across the now closed Atlantic to northwestern Africa, and through Spain, France, and Germany into Central Europe. They were the heart of Pangea, a vast high-altitude barrier that would have a profound and devastating impact on the climate of the new supercontinent. Today, after 300 million years of relentless erosion by wind, water, and ice, only the deep, gnarled roots of this once mighty range remain. In North America, they are the familiar gentle folds of the Appalachian Mountains. In Europe, they are the scattered uplands of the Variscan Belt, the rolling hills of Brittany in France, the Black Forest in Germany, the plateaus of the Czech Republic. When we walk through these ancient, worn-down mountains today, we are walking through the very core of a collision that forged a supercontinent. We are treading on the remnants of peaks that once pierced the sky at Himalayan heights. But Pangea was still not quite complete. While Euramerica and Gondwana had been welded together to form the main body of the supercontinent, another large continent, Siberia, still lay separate to the east. Between Siberia and the eastern margin of Euramerica, the part we know as Baltica, lay yet another ocean basin, but this too was destined to close. As the main Pangean assembly was concluding, Siberia began to rotate and pivot, closing this final ocean. Sometime around 290 million years ago, it collided with Baltica. This final collision created the last great mountain range of Pangea, the Ural Mountains. The Urals, which today form the traditional boundary between Europe and Asia, are the eastern seam of Pangea. They are the suture line where the last major independent continent was welded into the whole. And with that final weld, the work was done. The assembly was complete. Around 250 million years ago, at the boundary between the Permian and Triassic periods, for the first time in over 500 million years, nearly all of the Earth's continental crust was gathered together into a single magnificent and monstrous landmass. The impetus was gone. The Rhythmic Ocean was gone. The oceans that had once separated Siberia were gone. Pangea was born. It stretched from the South Pole nearly to the North Pole, a giant C-shaped landmass cupped around the eastern Tethys Sea. The rest of the planet was covered by the single world-spanning ocean of Panthalassa. The collisions had ceased. The mountain ranges stood at their zenith. Jagged and immense, the Earth had been reshaped. The stage was now set for the next act in our planet's drama. But what kind of world was this? What would it have been like to stand on the surface of this new unified land? With the birth of Pangea came the birth of a new and extreme global environment, a world of vast deserts, monstrous monsoons, and profound climatic challenges that would shape the destiny of all life on Earth. We must now leave the story of Pangea's violent formation and step onto the soil of the supercontinent itself to explore the world that it created. Imagine a world map, but not the one we know. Erase the familiar, comforting blue of the Atlantic Ocean. Erase the Indian Ocean, the Arctic Ocean. Leave only one planet-spanning sea of unimaginable size. Now take all the continents, all the familiar shapes of our world, and gather them together. Squeeze them into a single colossal landmass that stretches from the ice of the South Pole almost to the ice of the North. This is the world at the end of the Permian period, 250 million years ago. This is the world of Pangea. The titanic collisions have ceased. The grinding of continents has fallen silent. The final sutures of the Ural Mountains in the east, and the great central Pangean mountains in its heart, have been raised to their full Himalayan glory. The dust of their creation, a process that took longer than the entire age of mammals, is beginning to settle. For the first time in over 500 million years, the planet's land is functionally one. A new stage has been set. A new geography has been established, and with this new geography came a new climate. A climate of extremes, a climate more brutal, more severe, and more alien than almost anything our planet has experienced before or since. To understand the environment of Pangea, we must first grasp a simple fundamental principle that governs our own world's weather. It is the concept of continentality. Think for a moment of two cities in our modern world, located at roughly the same latitude. Think of Dublin, Ireland, and Krasnoyarsk, in the heart of Siberia. Dublin, perched on the edge of the Atlantic Ocean, experiences a mild, temperate climate. Its winters are chilly but rarely frozen solid. Its summers are warm but rarely scorching. The ocean acts as a colossal thermal battery. In the summer, the vast expanse of water absorbs the sun's heat slowly, keeping the coastal air cool. In the winter, it releases that stored heat just as slowly, preventing the temperatures from plunging too deeply. The ocean is a moderator, a great stabilizing force. Now travel thousands of miles inland to Krasnoyarsk. Here, far from the moderating influence of any ocean, the climate is one of savage extremes. Summers are hot and brief. Winters are epically, legendarily cold, with temperatures that can plummet to -50 degrees Celsius. There is no oceanic battery here to store and release heat. The land heats up rapidly under the summer sun and loses its warmth just as rapidly to the blackness of the winter sky. This is continentality. The further you are from the ocean, the more extreme your climate becomes. Now, take this principle and apply it to Pangea. This was not a continent like our modern ones. This was a supercontinent. The distances were almost beyond our comprehension. From the western shores of Pangea to its eastern heartland, one could travel for thousands upon thousands of miles without ever seeing a significant body of water. The very center of this vast landmass was the most remote place from an ocean that has ever existed on Earth. The result was a continental climate of an intensity that verges on the unimaginable. The heart of Pangea would have been a land of profound, world-defining extremes. The summers would have been scorching, not just hot, but lethally hot. With no oceanic breezes, no cooling sea fogs, the sun would have beaten down upon a dry, rocky landscape day after day, month after month, likely pushing temperatures in the deep interior to 50, perhaps even 60 degrees Celsius, 140 degrees Fahrenheit. It would have been a planetary-scale furnace. The winters would have been the mirror image, equally brutal. The land, having baked all summer, would radiate its heat away with shocking speed during the long nights and the low sun of winter. Temperatures would have plunged far below freezing, bringing deep, bitter and bone-dry cold to the heartland. This cycle of a blistering summer and a frigid winter would have been the dominant rhythm of life if life could exist there at all. But the extremity did not end with temperature. The other, perhaps more significant consequence of Pangea's immense size was a profound and deadly aridity. The heart of Pangea was not just a place of extreme temperatures, it was a desert on a scale that makes our modern Sahara look like a modest garden. Two factors conspired to create this great planetary desert. The first was simple distance. Air masses moving inland from the coast would have had to travel for thousands of miles, dropping their moisture as rain long before they ever reached the continent's interior. But the second factor was even more significant. It was the mountains. The great central Pangean Mountains, the colossal range forged by the collision of Gondwana and Euramerica, stood as a monumental barrier. This chain of 30,000-foot peaks ran along the equator, right across the heart of the supercontinent. It created a vast and inescapable rain shadow. Imagine the process. Winds, laden with moisture evaporated from the warm waters of the Panthalassic Ocean, would flow towards the land. As they reached the coast and hit the foothills of the central Pangean range, they would be forced to rise. As the air rises, it cools, and as it cools, it can no longer hold its moisture. The water vapor condenses into clouds and then falls as rain. A torrential, unending rain that would have drenched the windward coastal side of the mountains. But by the time this air had crested the mighty peaks and begun to descend on the other side, it was utterly changed. It was now a dry, moisture-starved wind. As it sank, it would warm up and compress, further reducing its humidity. This dry, descending air would sweep across the vast interior of Pangea, but it brought no rain. It only brought more heat, and an unquenchable thirst. It was a wind that took moisture, but never gave it. The entire interior of the supercontinent, an area likely larger than the whole of modern Asia, was trapped in the permanent dry grip of this immense rain shadow. The evidence for this great Pangean desert is written clearly in the geological record, in the rock strata corresponding to the Permian and Triassic periods. Geologists find vast, thick deposits of what are called Aeolian sandstones. These are sandstones formed not from river sediments or beach sands, but from wind-blown sand dunes. The fine, well-sorted grains and the distinctive sweeping cross-bedded patterns are the unmistakable signature of ancient dune seas or ergs, and in the heart of where Pangea once stood, these fossilized deserts are hundreds, even thousands of feet thick, testifying to a desert landscape that persisted for tens of millions of years. Alongside the sandstones we find another crucial piece of evidence: vast deposits of evaporites. These are minerals like halite, common salt and gypsum that are left behind when large bodies of water evaporate completely. The existence of thick layers of these salt deposits indicates that any lakes or inland seas that did exist in the Pangean interior were subjected to such intense evaporation that they simply dried up, leaving behind nothing but a brilliant white crust of salt stretching to the horizon. While the interior baked and froze in its arid prison, the coastal regions of Pangea experienced a different but equally extreme form of climate. They were governed by the most powerful monsoon system the world has ever known. A monsoon is a seasonal wind driven by the dramatic difference in how land and water heat up. In the summer, a continent heats up much faster and to a much higher temperature than the surrounding ocean. This creates a vast area of low atmospheric pressure over the land. Nature abhors a vacuum, and this low pressure acts like a giant engine, sucking in the cooler, wetter, higher pressure air from over the ocean. As this moisture-laden air is pulled inland, it dumps its water as torrential seasonal rain. In the winter, the situation reverses. The land cools down much faster than the ocean, creating a zone of high pressure that pushes cool, dry air outwards back towards the sea. On Pangea, this effect was amplified to a terrifying degree. The sheer size of the landmass meant the temperature difference between the supercontinent and the superocean of Panthalassa was extreme. In the summer hemisphere, Pangea would become a planetary-scale hot plate, creating a low-pressure system so vast it would have dominated the global climate. This would have drawn in gargantuan volumes of wet air from the surrounding ocean, particularly from the warm equatorial Tethys Sea that indented its eastern side. The result would have been a mega monsoon. For half the year, the coastal and near-coastal regions of Pangea would have been subjected to a wet season of biblical proportions. Not gentle spring showers, but months of relentless, violent torrential downpours. The landscape would have been transformed into a world of flash floods, of immense churning chocolate-brown rivers overflowing their banks, and of vast swampy floodplains. Then, just as dramatically, the season would shift. As the hemisphere tilted into winter, the land would cool rapidly, the pressure systems would reverse, and the rains would cease. Utterly, the wet season would be replaced by a long, harsh, dry season. The same landscapes that were drowning just months before would now bake under a cloudless sky, the rivers shrinking to trickles and the floodplains cracking into dry mud pans. This brutal cycle, from epic flood to epic drought, year after year, century after century, was the reality of life on the Pangean coast. So let us take a brief journey across this world of extremes. Let us walk from the coast to the continental interior. We begin on the shores of the Tethys Sea. It is the height of the wet season. The air is thick, hot, and heavy, with a humidity of nearly 100%. The sky is a dark, bruised grey, and a ceaseless roaring rain hammers the landscape. The ground is a morass of mud and standing water. Hardy, resilient forests of fern-like plants and early conifers survive here, their roots adapted to anchor them in the unstable, saturated soil. Now we travel west, inland, climbing into the foothills of the great central Pangean mountains. We are on the windward side. The rain here is even more intense. Waterfalls of an incredible scale plunge from the high cliffs, and powerful, violent rivers far larger than any Amazon or Nile carve immense canyons through the rock, carrying billions of tons of eroded sediment down towards the sea. The sound of the water is a constant, deafening roar. We climb higher, into the cold, thin air of the peaks themselves. We are above the clouds now in a world of rock and ice. For even on the equator, mountains this high would have sported immense glaciers. From here we look westward, out over the continental interior, and we see the rain shadow. The clouds do not follow us. They stop at the mountain crest as if hitting an invisible wall. Beyond, the sky is a hard, brilliant, cloudless blue. We descend the leeward slopes. The air becomes warmer and drier. The great rivers are gone. Here there are only ephemeral streams, dry, boulder-choked channels that might rage with flash floods a few times a century when a stray storm somehow manages to crest the peaks, but which are otherwise silent and empty. The lush vegetation gives way to hardy scrubland, then to sparse grasses, and then to nothing. We are now in the great interior, and it is a vision of hell. We stand on the shore of a vast salt pan, a white, blinding plain of cracked salt that shimmers under the oppressive heat. In the distance, rising from the shimmering air, is a sea of sand, not yellow but a deep, rusty red, colored by the oxidized iron in the sediment. These are not small dunes but vast, flowing mountains of sand, some of them hundreds of feet high, marching slowly in the hot, dry wind. There is no water, there is no cloud, there is no sign of life, save perhaps for the scuttling track of some desperate heat-adapted insect. The silence is absolute, broken only by the faint, whispering hiss of the wind blowing sand from the crest of a dune. This is the heart of Pangea, a desert larger than any nation, more hostile than any place on Earth today. And what of the oceans? The single global ocean of Panthalassa would have been a world unto itself. Its sheer size meant that ocean currents would have behaved differently. A single massive gyre, a rotating current of planetary scale, would have dominated its circulation, likely creating vast, stable zones in its center that were poor in nutrients. Its storms, with an uninterrupted fetch of thousands of miles to build, would have been hurricanes and typhoons of a power we can scarcely conceive. And nestled in the great sea-shaped bight of eastern Pangea was the Tethys Sea. This was the warm, tropical heart of the marine world. More sheltered than the vast Panthalassa, its waters would have been a crucible of life. a shallow, sunlit sea that would in the coming eras become the birthplace of many of the great marine reptile dynasties. This then was the physical world of Pangea, a planet of one land, one ocean, a world of brutal, uncompromising juxtapositions, drenching monsoons on the coast, and a permanent baking drought in the interior, searing summers and freezing winters. It was a world hostile in many ways to life as we know it. The very geography of the supercontinent had created an environment more extreme than almost any other in Earth's history. The question that burns then is this: who lived here? What manner of plants and animals could possibly adapt to, and even thrive in, such a relentlessly harsh world? To answer that, we must now populate this dramatic and desolate landscape. We must meet the strange and tenacious inhabitants of the late Permian world, the creatures who walked the soil of Pangea just before a cataclysm would change the face of life on Earth forever. The world of Pangea was a crucible, a planet of profound harshness, forged by the very tectonics that had brought it into being. Its vast, arid heartland, locked in a permanent rain shadow and subject to the punishing extremes of a continental climate, was a furnace in summer and a deep freeze in winter. Its coasts, meanwhile, were prisoners to the most violent monsoon cycle in Earth's history, swinging wildly between months of drowning deluge and months of parched, cracking drought. It was a world that seemed in many ways fundamentally hostile to the persistence of life. And yet, life is tenacious. Life is a force of incredible resilience and ingenious adaptation. Where there is even a sliver of opportunity, a niche to be exploited, life will find a way. And on Pangea, despite the immense challenges, life did not just survive for millions of years, it thrived. It created ecosystems of a complexity and strangeness that are difficult to comprehend. To walk across the landscapes of the late Permian period, about 260 million years ago, would be to enter a world that was not a desolate wasteland, but a vibrant, living planet, populated by a caste of creatures that were utterly alien to our modern eyes. Before we meet the animals, we must first build their world. We must first paint the landscape with the flora that formed the foundation of these ancient ecosystems. This was not a world of soft, green, grassy meadows. Grass had not yet evolved. It was not a world of vibrant, fragrant flowers or sweet, fleshy fruits. The angiosperms, the flowering plants that dominate our modern world, were still more than 100 million years in the future. This was instead the great age of the gymnosperms, the plants of the naked seed. These were rugged, hardy pioneers, and their very nature made them perfectly suited to the challenges of Pangea. Unlike the more primitive ferns that needed standing water to reproduce, the gymnosperms had mastered the art of the seed and the pollen. A seed is a marvel of evolutionary engineering, a tiny embryonic plant packaged with its own food supply and wrapped in a tough protective coat. It can lie dormant for months or even years, waiting for the brief window of moisture brought by the seasonal rains. Pollen, the male gainate, could be carried on the wind, freeing these plants from their reliance on water and allowing them to colonize the drier interiors of the great continent. The undisputed kings of the Pangean flora were the early conifers. Vast, somber forests of these trees would have stretched across the semi-arid uplands. We must not picture the lush, diverse pine forests of today, but something more monotonous, more primeval. These were trees built for survival. They possessed tough, waxy needles that were highly efficient at preventing water loss during the long, dry seasons. Their conical shape was robust, capable of withstanding the strong, dry winds of the continental interior. They were the silent, stoic sentinels of the Pangean landscape, clinging to life in a world that was often unforgiving. In the great southern portion of the supercontinent, the former lands of Gondwana, a different type of plant held sway. This was the domain of the seed ferns, or petroidosperms. The most important of these was Glossopteris, the very plant whose fossil distribution had been a cornerstone of Wegener's evidence for continental drift. These were not true ferns, but they had fern-like leaves, Crucially, they bore seeds, allowing them to dominate the vast, cool, temperate plains of southern Pangea. For thousands of miles, the landscape would have been covered in dense thickets and low forests of Glossopteris, its tongue-shaped leaves carpeting the ground, forming the primary food source for the great herbivorous animals of the south. Alongside the conifers and seed ferns, other ancient lineages grew. There were the cycads with their stout, woody trunks and crowns of stiff, palm-like leaves. They looked like short, squat palm trees but were entirely unrelated, their lineage ancient even then. And there were the first ginkgos, trees whose distinctive fan-shaped leaves are almost identical to their sole living relative, the ginkgo biloba tree, which we can still see in parks and cities today. To look upon a living ginkgo is to look upon a true relic of this lost Pangean world, a survivor that has persisted almost unchanged through 250 million years of planetary upheaval. And what of the older, more primitive plants? The great spore-bearing flora of the preceding Carboniferous period, the age of coal swamps. They had not vanished entirely, but their kingdom had been drastically reduced. The giant club mosses, the towering horsetails, these plants were still tied to the necessity of standing water for their reproductive cycle. On a world as predominantly dry as Pangea, they could no longer dominate. They were relegated to the margins, to the places where water was abundant and reliable. They would have formed dense, swampy, almost impenetrable jungles along the riverbanks, in the deltas, and across the coastal plains that were drenched year after year by the mega monsoon. To step into one of these Pangean swamps would be to step back in time into a dark, humid, primeval world of giant ferns and bizarre tree-sized horsetails, a world that was a faint echo of a bygone era. This, then, was the stage, a world of dark conifer forests, vast seed fern prairies and dense coastal swamps. And upon this stage walked a caste of animals so successful and diverse that they reigned over the earth for tens of millions of years. But if you are picturing dinosaurs, you must erase that image from your mind. The dinosaurs had not yet arrived. Their time was still to come. The rulers of late Permian Pangea were another group entirely, a group known as the Synapsida. We often hear them referred to by the misleading name, mammal-like reptiles. They were not true reptiles, they were in fact our own distant ancestors. The synapsids represent a distinct evolutionary line that diverged from the true reptiles very early on. They are defined by a key feature in their skull, a single opening or fenestra behind the eye socket, which served as an attachment point for powerful jaw muscles. The line of true reptiles, the sauropsids, would later develop two such openings, leading eventually to lizards, crocodiles and dinosaurs. But the single opening synapsids got a head start, and by the Permian period they had radiated into every conceivable terrestrial niche. They were the dominant land animals on the planet. To journey through Pangea would be to witness the zenith of the age of synapsids. Let us meet the great herds that populated its plains. The most abundant and successful herbivores of this time were a group known as the Dicynod. Their name means two dog teeth, and it refers to their most distinctive feature. They were bizarre-looking creatures, possessing a turtle-like beak, and in most cases only a single pair of teeth in their entire head, two large prominent tusks growing down from the upper jaw. The most famous of these was Lystros, the pig-sized creature whose fossils were found from Africa to Antarctica, but it was just one of many. There were Dicynons of all sizes, from small burrowing forms the size of a mole rat to giant lumbering beasts like Canamaieria, which evolved slightly later and was as large as a modern hippopotamus, with a massive head and powerful shoulders for digging up roots and tubers. They were stout, barrel-chested, and slow-moving. They likely wandered the semi-arid plains in vast herds, much like the wildebeest or bison of today, their horny beaks perfectly adapted for snipping the tough, fibrous Pangean vegetation. Sharing the landscape with them were other, even stranger herbivores. These were the parasaurs, whose name means cheek lizard. These were the armored tanks of the Permian. A creature like Scutosaurus, whose name means shield lizard, was a true behemoth. It was about 10 feet long with a massively built, bulky body, held up by thick, elephantine legs. Its most striking feature was the armor. Its skull was adorned with bony knobs and flanges, and its back was covered in bony plates, called osteoderms, embedded directly in the skin, creating a formidable defensive shield. They were slow, ponderous animals, likely browse on low-lying vegetation in the river valleys. Where there are herds of herbivores, there must also be predators, and the apex predators of Pangea were creatures of nightmare. They were a terrifying group of synapsids known as the Gorgonopsians. Their name, meaning gorgon face, is a fitting one. These were the saber-toothed tigers of the Permian, fast, powerful, and built for the kill. They represented the pinnacle of synapsid evolution. Picture a creature like Inostransvia, one of the largest of the group, found in what is now Russia. It was the size of a large bear with a long, lean, powerful body and a massive, elongated skull nearly 2 feet long, and from its upper jaw protruded a pair of immense dagger-like canine teeth. These were the first true saber-toothed carnivores in the planet's history. They were not for show. These teeth were for stabbing and slicing, for gripping struggling prey and inflicting catastrophic wounds. The Gorgonopsians were the wolves and lions of their day, likely hunting in packs to bring down the large Dicynot and ants and armored perisaurs that were their main source of food. But the Gorgonopsians were not the only carnivores. Occupying other predatory niches were the Thoracocephalians, or beast-heads, another diverse group of synapsids, generally smaller and more slender, perhaps filling the role of foxes, weasels, or wild dogs in the Pangean ecosystem. And then there was one other group of synapsids. At a glance they might not have seemed as impressive as the giant Gorgonopsians or the tusked Dicynodonts, but they were, in many ways, the most significant animals on the entire planet. They were the cynodonts, the dog teeth. This group was the most mammal-like of all. They had developed highly differentiated teeth, incisors for nipping, canines for gripping, and complex multi-cuspid molars for chewing and processing food efficiently. Their posture was more erect and mammal-like, with their legs positioned more directly underneath their bodies for more efficient movement. Microscopic examination of their fossilized snouts shows a rich network of pits and holes, identical to those that house the sensitive whiskers on the snout of a modern dog or cat, suggesting that cynodonts themselves had evolved whiskers, a key sensory tool. While the Gorgonopsians ruled the present, the cynodonts held the key to the future. It was from this unassuming group of small to medium-sized predators and omnivores that, millions of years later, the first true mammals would evolve. The world of Pangea was not exclusively a synapsid world, however. The other great lineage of land vertebrates, the true reptiles or sauropsids, were also present, though they were very much living in the shadows of their synapsid rulers. The ancestors of lizards, snakes, and turtles were skittering through the undergrowth, and another, more significant group was beginning its rise. These were the early archosaurs, the ruling reptiles. In the Permian they were mostly small, nimble, lizard-like creatures, but this group held immense potential. It was the lineage that would in the next geologic era explode to produce the crocodiles, the flying pterosaurs, and most fearsome of all, the dinosaurs. And what of the waters? In the great rivers and monsoon swamps of the coastal plains, life took on a different character. Here, giant amphibians were the apex predators. Creatures like Priunosuchus, found in modern Brazil, were a terrifying sight. It was a temnospondyl amphibian, but it was superficially identical in size and lifestyle to a modern crocodile. Reaching lengths of up to 30 feet, it was one of the largest amphibians of all time, a silent, ambush predator lurking in the murky Pangean waterways. Out in the oceans of Pamphalassa and the warm Tethys Sea, life was also abundant, though it was a very different cast of characters than in our modern seas. The reefs were not built by the corals we know today, but by communities of sponges, branching moss-like animals called bryozoans, and calcareous algae. The seafloor was dominated by creatures like brachiopods, which resembled clams but were from a different phylum entirely, and by vast waving gardens of crinoids or sea lilies, animals related to starfish that rooted themselves to the seafloor with a long stalk, and scuttling in the depths were the very last of the trilobites. This great class of arthropods, which had dominated the planet's oceans for over 250 million years, was now faded, its diversity depleted, a final ghost-like remnant of a more ancient world, unknowingly living out its final days. This then was the world of late Permian Pangea, a complex, vibrant and successful world, a world ruled by tusked herbivores and saber-toothed carnivores, a world of hardy conifer forests and vast fern prairies, a world that had achieved a state of ecological equilibrium that had lasted for millions of years. It seemed permanent, it seemed stable, it seemed destined to continue forever. But it was not. This entire intricate and deeply ancient world was standing on the edge of a cliff. A catastrophe was coming, an extinction event so profound, so devastating, so nearly absolute, that it would forever reset the course of life on our planet. The very forces that had assembled Pangea had also set a time bomb at the heart of the global ecosystem, and that bomb was about to detonate. The world of the synapsids was about to end in fire and suffocation, in an event now known to science by a simple, chilling name, the Great Dying. Look once more upon the world of late Permian Pangea. See the herds of Lystrosaurus and Canamaeria grazing on the vast plains of Glossopteris. See the fearsome Inostrance Via, its saber-like fangs glinting in the pale sun, stalking its prey through the hardy conifer forests. Hear the buzz of strange insects, the splash of giant amphibians in the murky rivers. It is a world full of sound and motion, a world of intricate food webs, of predator and prey, of life carrying on its ancient, bloody and beautiful business, as it had for eons. Now try to imagine a great silence falling upon this world. Imagine the forests withering, the trees falling to rot with no creature to eat them. Imagine the herds vanishing, the plains emptying. Imagine the oceans once teeming with life, turning stagnant and still. This is not a fantasy, it is what happened. Around 252 million years ago, at the boundary between the Permian and Triassic periods, our planet experienced the most profound biological crisis in its entire 4.5 billion year history. This was not just another extinction event. We often think of the asteroid impact that wiped out the dinosaurs as the ultimate planetary catastrophe, but what happened at the end of the Permian was incomparably worse. It was a mass extinction so severe, so utterly devastating, that it has come to be known by a simple, terrible and wholly appropriate name, the Great Dying. The statistics behind this event are staggering to the point of being almost incomprehensible. Scientists who study the fossil record estimate that in the oceans up to 96% of all species vanished forever. 96%. It was a near total sterilization of the seas. The last of the trilobites, who had survived for over 250 million years, were gone. The great seafloor covering reefs built by sponges and bryozoans collapsed and disappeared. Entire classes of marine animals were wiped out. On land, the devastation was scarcely less severe. At least 70% of all terrestrial vertebrate species became extinct. The great synapsid dynasties that had ruled the planet for 60 million years were shattered, their reign brought to an abrupt and brutal end. In the space of a geological instant, the living world was brought to its knees. Life on Earth came perilously, terrifyingly close to being extinguished altogether. For decades, the cause of this incredible catastrophe was one of the greatest mysteries in all of science. There were dozens of theories. An asteroid impact, a nearby supernova, a sudden release of methane from the seafloor. But as evidence accumulated, a consensus began to form around a single terrestrial culprit. The killer, it turned out, came not from the depths of space, but from the depths of the Earth itself. The primary suspect for orchestrating the Great Dying is a geological feature located in modern-day Russia, a feature known as the Siberian Traps. The name is deceptively mundane. The word traps has nothing to do with a snare. It comes from the old Swedish word trappa, meaning stairs or steps, which describes the step-like terraced landscape that these formations create. But what they represent is anything but mundane. The Siberian Traps are the remnants of one of the largest known volcanic episodes in the history of our planet. We must erase from our minds the image of a single cone-shaped volcano like Mount Fuji or Mount St. Helens. The Siberian Traps event was something else entirely. It was a flood basalt eruption. For a period of time that may have lasted close to 1,000,000 years, the very crust of the Earth in this region split open. Immense fissures, some of them hundreds of miles long, ripped through the landscape, and from these gaping wounds lava poured forth, not in explosive, ash-filled eruptions, but in vast, relentless, flowing floods of incredibly hot, fluid basalt. The scale of this event is difficult to articulate. Wave after wave, flood after flood of molten rock, some of them thousands of feet thick, poured out across the land, incinerating everything in their path. They filled valleys, buried hills, and spread out to create a vast new plateau of black volcanic rock. Over the course of the eruption, an area of what is now Siberia, larger than the entirety of Western Europe, an area of over 7 million square kilometers, was buried under this sea of lava. The total volume of erupted material is estimated to be at least 4 million cubic kilometers. It is enough molten rock to cover the entire continental United States in a layer of lava nearly half a kilometer deep. For hundreds of thousands of years, the sky over a vast portion of Pangea would have been a permanent hellish orange-red, choked with volcanic smog, and the land itself would have been a sea of fire, a landscape of immense flowing rivers of liquid rock. What could have possibly triggered such a cataclysm? The answer seems to lie with Pangea itself. The leading theory today points to the formation of a mantle plume. As we have discussed, the assembly of the supercontinent created a huge insulating blanket over the mantle. Heat, unable to escape effectively, built up over millions of years. This may have led to the formation of a colossal plume of superheated, buoyant rock deep within the Earth's mantle, which began to rise, like a hot air balloon ascending through water. When this immense plume head, hundreds of kilometers in diameter, finally reached the base of the lithosphere beneath Siberia, it began to melt its way through. The result was the apocalyptic flood basalt eruption. The formation of Pangea had loaded the gun, the mantle plume had pulled the trigger. But even an eruption of this biblical scale does not by itself explain a global extinction event that killed 96% of marine life. The lava flows themselves were a regional catastrophe, not a global one. The true kill mechanisms were not the lava, but the immense cocktail of gases and aerosols that were blasted into the atmosphere, relentlessly for up to 1,000,000 years. The Siberian Traps were a planetary chemical weapon, and they unleashed a devastating multi-stage assault on the global ecosystem. The first stage of the attack was likely a brief but brutal volcanic winter. The eruptions would have belched immense quantities of sulfur dioxide and fine ash into the stratosphere. These particles would have created a global haze, reflecting sunlight back into space and causing a sharp, sudden drop in global temperatures. Photosynthesis would have been hindered, and the base of the food chain would have been severely stressed. But this was just the opening salvo. This sulfur dioxide would have combined with water vapor in the atmosphere to create sulfuric acid. This would then fall back to Earth as intense, unrelenting acid rain. This rain would have been strong enough to burn the leaves of plants, to poison the soil by leaching away vital nutrients, and to severely acidify freshwater lakes and the surface layers of the ocean, killing sensitive organisms. The fossil record of this time shows a fungal spike, a layer of rock almost entirely devoid of plant pollen but containing an overwhelming abundance of fossilized fungal spores. It is the signature of a dead and rotting world, a world where the forests have died on a continental scale and the fungi have inherited the earth, feasting on the decay. This initial phase of cooling and acid rain was devastating, but it was the second stage that delivered the knockout blow. The crucial, fatal detail of the Siberian Trap's eruption was its location. The magma did not just erupt through inert volcanic rock, it burned its way through one of the largest sedimentary basins on Earth, a basin rich in immense ancient deposits of coal, oil and natural gas, as well as carbonate rocks like limestone. The intense heat of the magma essentially cooked these vast fossil fuel reserves in situ, vaporizing them and releasing their stored carbon directly into the atmosphere. The result was the injection of a truly astronomical quantity of greenhouse gases, carbon dioxide, and even more potently, methane into the global atmosphere. After the initial cooling effect of the sulfur aerosols wore off, this immense greenhouse gas blanket began to take effect. The planet began to warm, and it warmed with a speed and intensity that the global ecosystem simply could not handle. This was the main killer, a rapid runaway greenhouse effect. Global average temperatures are estimated to have soared by at least 5 degrees Celsius, and perhaps by as much as 10 degrees or more. The equatorial regions may have become lethally hot for most forms of complex life. But the most insidious effects of this warming were felt in the oceans. As the planet's atmosphere and surface waters heated up, the oceans began to stratify and, more importantly, they began to lose their ability to hold dissolved oxygen. It is a simple law of physics: warmer water holds less gas. As the oceans warmed, they began to suffocate. This process, called ocean anoxia, would have been catastrophic for the vast majority of marine animals who, like us, require oxygen to breathe. The deep ocean, its circulation sluggish due to the Pangean continental arrangement, would have been the first to become a vast oxygen-starved dead zone. But it gets worse. As these deep waters became anoxic, they became a paradise for a different kind of life, anaerobic bacteria. Specifically, sulfate-reducing bacteria that thrive in oxygen-free environments. These microbes do not breathe oxygen, they breathe sulfate, and as a metabolic byproduct, they produce immense quantities of a deadly poisonous gas, hydrogen sulfide haze. Imagine the scene. The deep oceans of the planet, now devoid of oxygen, are being filled with this toxic, foul-smelling gas. The water itself would have turned into a poisonous soup. The vibrant blue of the deep sea may have been replaced by a sickening pink or purple hue, the color of the sulfur-loving bacteria that now reigned in the abyss. This was the horrifying purple ocean of the Great Dying. For a time, this poison was trapped in the deep ocean, but as the anoxia intensified and the concentration of hydrogen sulfide grew, it is thought that this toxic gas began to bubble up from the depths, erupting into the atmosphere itself. This would have been the final, apocalyptic kill mechanism. Hydrogen sulfide is incredibly toxic to both plants and animals on land. A massive release of this gas would have poisoned the very air, causing the remaining terrestrial ecosystems to collapse. Furthermore, atmospheric hydrogen sulfide attacks and destroys the ozone layer, the planet's protective shield against lethal ultraviolet radiation from the sun, would have been shredded, exposing any surviving life on the surface to deadly levels of UV, causing mutations and killing off even the hardiest of creatures. The Great Dying was not a single event, but a cascade of horrors, a domino effect of environmental collapse triggered by a single immense volcanic event. A volcanic winter and acid rain killed the forests. A runaway greenhouse effect baked the planet. The oceans warmed and suffocated, turning into a purple, toxic cesspool, and finally that oceanic poison may have erupted into the air, delivering the final coup de grace. The aftermath was a silent world. The Permian ecosystems were not just damaged, they were annihilated. The great Gorgonopsian predators were gone forever. The Pariasaurs, the armored tanks, were gone. The vast majority of the Dysononts were gone. The trilobites, the sea scorpions, the great reef systems, all gone. The planet was a desolate, empty hothouse. The fossil record shows a coal gap for millions of years after the extinction, indicating that there were simply not enough trees left on the entire planet to form coal deposits. But life, battered and broken, had held on by the barest of threads. In the ecological wasteland of the early Triassic, a few hardy survivors emerged from their burrows and hiding places to find a world empty of competition, empty of predators. The most notable of these was Listros of tusked, pig-sized Dicynodont. For some reason, perhaps its burrowing habits or its efficient respiratory system, allowed it to tolerate the low oxygen atmosphere. It had survived the apocalypse, and in the empty world that followed, its populations exploded. For a time, 90% of all land vertebrates on Earth were this one single genus. It was a world of disaster taxa, of hardy generalists inheriting a sterilized planet. The Great Dying was a profound reset. It was the definitive end of the Paleozoic era and the ancient world it represented. The reign of the synapsids was over. The slate had been wiped clean, but this ending, as terrible as it was also a beginning. The extinction had created a vacuum. The old rulers were dead, and into this vast, empty ecological space, a new group of survivors, the archosaurs, the ruling reptiles who had been minor players in the Permian, would now begin to radiate, to evolve and to rise. The death of the old world had cleared the stage for the birth of a new one. The Mesozoic era, the age of reptiles, and the reign of the most famous and charismatic animals in Earth's history, the dinosaurs, was about to begin. Imagine standing on a shore 251 million years ago. In the immediate aftermath of the Great Dying, the air is thick, hazy, and oppressively hot, still choked with the greenhouse gases of the Siberian Traps eruptions. The sun is a pale, sickly disk behind a perpetual chemical smog. The silence is the most profound feature. The great forests of the Permian are gone, replaced by vast, rotting plains of dead wood, a world dominated by the silent work of fungi. The teeming herds of Dicynodonts and the terrifying Gorgonopsian predators that hunted them have vanished as if they had never been. The complex music of a healthy ecosystem has been replaced by a low, monotonous hum. This is the world of the early Triassic. It is a ghost world, a planetary patient in critical condition. The recovery from the Permian Triassic extinction was not a swift or triumphant rebound. It was a slow, painful, and protracted process that lasted for millions, perhaps even 10 million years. The planet's systems were fundamentally broken. The carbon cycle was in chaos. The oceans were stagnant, oxygen-starved, and acidic. The intricate food webs that had taken tens of millions of years to build had been completely severed. Life had to begin again, almost from scratch. In the wake of mass extinctions, paleontologists often see a curious phenomenon known as the Lilliput effect. The complex ecosystems of large animals are gone, and for millions of years the world is dominated by creatures that are noticeably smaller, less diverse, and less specialized. These are the disaster taxa, the hardy generalists who were robust enough, or perhaps just lucky enough, to weather the storm. And the poster child for the early Triassic disaster world, the ultimate survivor of the Great Dying, was our old acquaintance, Lystrosaurus. For reasons that scientists still debate, perhaps its semi-burrowing lifestyle allowed it to shelter from the worst of the atmospheric poisoning. Perhaps its efficient respiratory system was well suited to the low oxygen conditions, or perhaps it was simply its unfussy, root-eating diet. Lystrosaurus had pulled through the apocalypse, and in the empty world that it inherited, it exploded. With its predators gone and its competitors eliminated, this humble, pig-sized, tusked herbivore became the most abundant terrestrial vertebrate on the entire planet. Its fossils are found everywhere from Russia to China, from South Africa to India and Antarctica, providing in its own way further stunning proof of the Pangean land connection. For a few million years, to walk across the landscape of Pangea would be to see vast, monotonous herds of this single, ungainly creature. This incredible abundance of a single species is not a sign of a healthy ecosystem. It is the sign of a broken one. a world where the web of life had been reduced to a few tough threads. The slow process of rebuilding began with the plants. The great Glossoptes forests of the southern hemisphere were gone forever. In their place, new, even hardier types of seed ferns, particularly a group known as Dicroidium, began to spread, forming the new foundation of the recovering food chain. The conifers, with their inherent toughness and adaptations to dry conditions, also began a slow resurgence, gradually re-establishing vast hardy forests across the arid continental interior. But the recovery was slow. The coal gap, the period in the geologic record where no coal was formed, lasted for nearly 15 million years into the Triassic, a silent testament to a world largely devoid of dense, lush forests. In the poisoned oceans, the recovery was even slower. The beautiful, complex reef systems of the Permian, built by sponges and delicate bryozoans, were gone, and it would take nearly 10 million years for a new type of reef builder, the stony stalactinian corals that build our modern reefs, to evolve and begin their work. The seas were dominated by a few disaster taxa of their own, like vast swarms of the bivalve claria. The last of the trilobites were gone. The diverse communities of the Permian seafloor had been replaced by a low-diversity ecosystem, struggling to regain a foothold in the hostile anoxic waters. But as the millions of years crept by, the Earth's systems slowly began to heal. The excess carbon dioxide was gradually drawn down from the atmosphere, buried in sediments and absorbed by the recovering biosphere. The planet's temperature began to stabilize, the oceans began to re-oxygenate, and as the environment slowly became more hospitable, a new evolutionary story began to unfold. The old rulers of Pangea, the synapsids, were a shattered dynasty. The Great Dying had almost completely wiped them out. The Gorgonopsians were gone. The Periosaurs were gone. The vast majority of the Dicynauts were gone. This created a profound power vacuum. The ecological stage had been cleared of its lead actors, and into this vacant world, a new group of animals, a lineage that had been living in the shadows of the synapsids during the Permian, would now step forward to seize the opportunity. These were the archosaurs, the ruling reptiles. This group, which includes modern crocodiles and birds and the extinct dinosaurs and pterosaurs, had a number of key adaptations that made them uniquely suited to thrive in the harsh, dry world of Triassic Pangea. Their posture was more upright than the sprawling synapsids, allowing for more efficient movement. Their respiratory systems were more advanced, better at extracting oxygen from the thin air, and crucially, they had a more efficient method of water conservation, excreting waste as uric acid rather than water-heavy urea, a vital advantage in an arid world. The Triassic period was the beginning of the age of reptiles, but for most of it was not yet the age of dinosaurs. It was the age of the archosaurs, and for much of the Triassic, one particular branch of the archosaur family tree was dominant. This was the Crustacea, the lineage that includes all modern crocodiles and their vast diverse array of extinct relatives, and the Triassic Crustaceans were far more varied and spectacular than their modern semi-aquatic ambush predator cousins. They were the new rulers of Pangea. There were the phytosaurs, a group that looked and lived almost exactly like a modern crocodile lurking in the recovering rivers and lakes, a stunning example of convergent evolution where two unrelated groups independently evolved the same body plan to fit a similar niche. But the most impressive crustaceans were on land. There were the aetosaurs like the formidable Desmatosuchus. These were heavily armored herbivores, their bodies covered in a shell of interlocking bony plates, with a pair of massive curved horns sweeping out from their shoulders. They were the new reptilian tanks of the Triassic world, replacing the Periasaurs of old. And there were the apex predators. For much of the Triassic, the top carnivore on Pangea was not a dinosaur. It was a giant, terrestrial crocodile-line archosaur. Creatures like Postosuchus, found in what is now North America, were terrifying. It was a heavily built predator, up to 20 feet long, that walked on its two hind legs like a Tyrannosaurus rex, with a massive skull full of dagger-like teeth. It was the undisputed king of its environment. the top predator in the new Pangean ecosystems. The Cretaceans were the dominant force, but the other great branch of the archosaur family tree, the Avimetausalia, the lineage that would lead to birds and dinosaurs, was also beginning its evolutionary journey, living for the moment in the shadow of their dominant crocodile line cousins. One of the first great innovations of this line was the conquest of the air in the late Triassic. The first pterosaurs took to the skies. These were not dinosaurs but a closely related sister group. Creatures like Eudimorphodon were the first vertebrates to achieve powered flight, not by using feathers but with wings made of a leathery membrane of skin stretched from the side of their body to the tip of a single spectacularly elongated fourth finger. With their long toothy jaws they would have flitted through the coastal skies, snatching fish from the sea or insects from the air, pioneers of a new aerial ecosystem. And finally, on the ground, another group of Avimetausalia appeared. Sometime around 230 million years ago, in the part of Pangea that would one day become South America, the first true dinosaurs evolved. We must banish the popular image of colossal giants. The first dinosaurs were nothing of the sort. They were small, nimble, and relatively rare components of the fauna. Creatures like Echiraptor, the dawn plunderer, were barely 3 feet long. Ferrosaurus, one of the earliest large predatory dinosaurs, was formidable, but at 15 feet long it was still smaller than the great Cretacean predators like Postoscus with whom it shared its world. The early dinosaurs were bipedal, fast and agile, but for millions of years they were secondary players, living in a world dominated by their crocodile line relatives. Their time had not yet come. And what of our own lineage? What of the synapsids? They were not entirely extinguished. A few lineages had clung on through the great dying, but the world they now inhabited was a terrifying one, ruled by a new dynasty of giant reptiles. The surviving synapsids, mostly the adaptable cynodonts, responded to this new pressure in a way that would define our own origins. They adapted by becoming smaller. They became creatures of the night, hiding from the daylight world of the archosaurs. This shift into the nocturnal realm drove a suite of revolutionary new adaptations. They likely evolved endothermy, or warm-bloodedness, to stay active in the cool of the night. To conserve that body heat, they evolved the first true insulating coat of fur or hair. Their senses of hearing and smell became incredibly acute, essential for navigating and finding food in the dark. Their brains grew larger and more complex. They were becoming, for all intents and purposes, the first mammals. By the late Triassic, true tiny shrew-like mammals had indeed evolved from these cynodont ancestors, scurrying through the undergrowth of a world that belonged to the reptiles. And so, the stage for the remainder of the Mesozoic was set. Pangea was a world ruled by the diverse Cretacean archosaurs. The first small dinosaurs were cautiously carving out a niche. The first pterosaurs soared overhead, and our own tiny furry ancestors were hiding in the shadows, biding their time. It seemed that this new world order, the reign of the crocodile relatives, was set to last for eons. But the Earth was not finished. The planet that had been unified for so long was beginning to stir once more. And at the boundary between the Triassic and Jurassic periods, another global catastrophe, another mass extinction event would strike. It was not as severe as the Great Dying, but it was a cataclysm that would selectively and decisively reset the board once again. It would devastate the dominant Cretacean dynasty, but leave the upstart dinosaurs almost completely unscathed. The event that would finally clear the way for the age of dinosaurs was coming. And at the same time the supercontinent of Pangea itself was beginning to groan under the strain of the immense heat building beneath it. The great coming apart was about to begin. The world at the close of the Triassic period, some 201 million years ago, was a world reborn. The ghost of the Great Dying had finally begun to fade, and the planet was once again cloaked in a vibrant if strange tapestry of life. Pangea, though beginning to show the first signs of strain, was still fundamentally a single unified landmass. But its rulers had changed. The ancient synapsid dynasties of our own distant kin were gone. reduced to tiny, furtive creatures hiding in the shadows of the night. The new masters of the world were the archosaurs, the ruling reptiles. And among the archosaurs, the dominant lineage was clear. The Crotalans, the great crocodile-line archosaurs, were triumphant. Fierce, bipedal predators like Postosuchus were the apex carnivores. Armored atosaurs browsed on the tough vegetation. The world belonged to them. In this world, the dinosaurs were a sideshow, a promising but secondary group of smaller, nimbler animals, living in the niches left vacant by their more powerful cousins. From the perspective of the late Triassic, you would have no reason to bet on the dinosaurs. You would have assumed that the future of the planet belonged to the great Crotalans. But the history of life on Earth is not a smooth, predictable progression. It is a story punctuated by sudden, violent revolutions, and the planet was on the brink of yet another convulsion. The second great cataclysm of the Mesozoic era was looming, an event that would decisively and selectively rewrite the rules of life once again. And at the same time, the supercontinent itself, after more than 100 million years of unity, was beginning to tear at the seams. The final act of Pangea was to be a story of fire, extinction, and the great coming apart. The trigger for this next global crisis was, once again, volcanic, but this time the fire came not from Siberia, but from the very heart of Pangea itself. As the internal heat beneath the supercontinent continued to build, the crust began to stretch, thin, and weaken. This was particularly true in the equatorial region between what is now North America, South America, and Africa, and as the crust thinned, magma began to surge upwards. This was the birth of the Central Atlantic Magmatic Province, or CAMP. The CAMP eruption was, in terms of sheer volume, even larger than the Siberian traps. It was another colossal flood basalt event. For about 600,000 years, immense fissures ripped open across the heart of Pangea. From these cracks, which stretched for thousands of miles, truly unbelievable quantities of lava poured forth, covering an area of over 11 million square kilometers, an area larger than the entire country of Canada. Rivers of molten rock flowed across the landscape, burying everything. And just like the Siberian traps before it, the CAMP eruption unleashed a devastating cocktail of chemicals into the global atmosphere. The pattern of catastrophe was terrifyingly familiar. First, the immense quantities of sulfur dioxide would have created a brief, sharp volcanic winter and spawned torrents of acid rain, stressing ecosystems and poisoning the oceans. But this was merely the prelude. The main event was the release of gargantuan volumes of carbon dioxide, both from the magma itself and from the burning of subterranean fossil fuel deposits baked by the intrusions. The planet was once again thrown into a rapid, severe, and runaway greenhouse event. Global temperatures soared. The oceans began to warm and acidify. Anoxia, the suffocation of the seas, began to spread. The world was plunged into another mass extinction event. This was the Triassic-Jurassic extinction. It was not as utterly devastating as the Great Dying. Perhaps only 50% of all species went extinct, but it was incredibly selective, and its selectivity is the key to understanding the world that followed. For reasons that are still debated, this particular combination of climatic shocks, the acid rain, the sudden warming, the atmospheric chemistry, was especially devastating to the dominant Crotalan archosaurs. The great terrestrial crocodile relatives were all but wiped out. The giant amphibians in the rivers also suffered immensely. But miraculously, the dinosaurs seem to have weathered the storm almost perfectly. Why did the dinosaurs survive when their dominant cousins perished? The answer may lie in their unique physiology. Dinosaurs possessed a remarkably efficient bird-like respiratory system, with air sacs that allowed for a one-way flow of air through their lungs. This system is far more effective at extracting oxygen from the air than either a mammal's or a crocodile's. In the high carbon dioxide, low oxygen atmosphere of the extinction event, this superior respiratory system may have been the crucial life-saving advantage. While their competitors were struggling to breathe, the dinosaurs could still function effectively. Whatever the precise reason, The result was a planetary-scale changing of the guard. The Triassic-Jurassic extinction was the event that cleared the board for the dinosaurs. Their main rivals were gone. The top predator niches were empty. The large herbivore niches were empty. The world was theirs for the taking, and take it they did. As the planet slowly recovered in the dawn of the Jurassic period, the dinosaurs, now freed from their competitors, exploded in a spectacular evolutionary radiation. This was the true beginning of the age of dinosaurs. They began to grow to immense, awe-inspiring sizes. The sauropods, with their colossal bodies, whip-like tails, and impossibly long necks, evolved to become the largest animals ever to walk the earth. Great herds of Brachiosaurus and Apatosaurus would soon dominate the landscapes. The carnivorous theropods also grew to giant sizes, with predators like Allosaurus and Ceratosaurus becoming the new apex predators, filling the role once held by Prostosaurus. Armored dinosaurs like the plate-backed Stegosaurus and the bird-hipped ornithopods also diversified and spread across the globe. The reign of the dinosaurs had truly begun. And as this biological revolution was unfolding, the geological revolution that enabled it was accelerating. The camp eruption was not just the cause of the extinction, it was the birth cry of a new ocean. It was the sound of Pangea beginning to die. The stretching and thinning of the crust in the heart of Pangea was not a gentle process. It created immense rift valleys. These were long linear valleys where the continental crust was sinking and pulling apart. We can see a modern analogue today in the Great Rift Valley of East Africa. These Pangean rift valleys began to widen, and eventually the sea flooded in. At first these would have been narrow, shallow seaways. The hot, arid climate meant that this seawater would evaporate rapidly, leaving behind immense deposits of salt, which are found today buried deep off the coasts of the Atlantic. But the pulling apart continued, relentlessly. The narrow seaway eventually widened to the point where a true oceanic crust made of basaltic lava began to erupt in the center. A new young mid-ocean ridge was born. This was the birth of the Central Atlantic Ocean. This was the great primary sundering of the supercontinent. Pangea was being torn in two. The northern landmass of Laurasia, North America and Eurasia began to separate from the southern landmass of Gondwana, South America, Africa, Antarctica, Australia and India. After more than 100 million years of unity, the world was once again becoming a world of multiple continents. This breakup had profound consequences for the planet's environment and for the evolution of life. As the new ocean widened, it brought moisture deep into the heart of the arid supercontinent. The extreme hypercontinental climate of Pangea began to break down. The mega monsoons weakened and the climate became milder and wetter. The vast deserts began to shrink, replaced by lush forests and prairies of ferns and cycads. This new wetter climate may have been one of the factors that allowed the evolution of the immense sauropods, providing the vast quantities of vegetation needed to support their giant bodies. But the most significant consequence was isolation. As Laurasia and Gondwana drifted apart, the animals and plants living on them became separated. The cosmopolitan fauna of Pangea, where a creature like Listros could be found almost everywhere, was gone. Now life began to evolve down separate, unique paths on each of the drifting landmasses. The dinosaurs of Gondwana began to evolve into different forms than their cousins in Laurasia. This continental breakup became a great engine of biodiversity, creating the unique ecological signatures we see on each of our modern continents. The unraveling continued. Gondwana itself began to fracture, with Africa and South America pulling apart to form the South Atlantic. India broke away and began its long, lonely journey northwards towards its eventual collision with Asia. Australia and Antarctica rifted apart. The world we know today, a world of 6 continents and 5 oceans, was slowly, piece by piece, emerging from the ghost of Pangea. And so, our long journey comes to its end. We have travelled from the first hesitant idea in the mind of Alfred Wegener, a simple observation of a map. We have journeyed through the decades of scorn and scientific debate. We have plunged into the ocean depths to find the secrets of the seafloor and unlocked the fossilized magnetism that provided the final stunning proof. We have watched, over hundreds of millions of years, as lost continents collided to forge the mighty supercontinent of Pangea. We have explored its harsh climates and met its strange inhabitants. We have borne witness to its near death in the fires of the Great Dying, watched its brief reptilian rebirth, and have now stood witness to its final dramatic breakup. The legacy of Pangea is the world we live in, the mountains in your backyard, the oil and gas that power our civilization, the very shape of the nations on our maps, are all a direct result of this ancient history. The distribution of fossils, the migration patterns of animals, the currents of our oceans, all are echoes of this great supercontinent and its eventual sundering. And the story is not over. The dance of the continents continues. The Atlantic Ocean is still widening. The Pacific is still shrinking. Africa is slowly crushing the Mediterranean as it collides with Europe. The Himalayas are still rising as India pushes relentlessly into Asia. The plates are still in motion, driven by the same inexorable engine that assembled and destroyed Pangea. Scientists, using the laws of plate tectonics, now predict that in the distant future, perhaps 250 million years from now, the continents will come together once more. The Atlantic will close, the Americas will collide with a merged Afro-Eurasia, and a new supercontinent, sometimes called Pangea Ultima, will be born. The great cycle will begin again. The world of Pangea, therefore, is more than just a fascinating chapter from our planet's deep past. It is a fundamental part of our planet's identity. It is a testament to the immense, dynamic and ever-changing nature of the ground beneath our feet. It teaches us that nothing on Earth is permanent, not the mountains, not the oceans, not even the continents themselves. It is a story written in stone on a timescale that humbles our human experience. And it is a story that is still being written every day, in every earthquake, in every volcanic eruption, in the slow, silent and unstoppable drift of the continents.